Alright, hell yeah. So it feels good to be back. We're going to do a kinematics problem. So this is a projectile motion problem. You know what I mean? Something from the ground is thrown up into the air or projected up into the air. And that's kind of the basics. My videos typically average about an hour long. And I think what you can gain from this is, even just in the first 5 to 10 minutes, is I'm going to set up an approach of how I would solve it. So if this is one of the problems, you can read through it right now, that you're like, yeah, I would give it a go, you know what I mean? And you're not quite sure how you would do it, well, hell yeah, I'm going to show you the simplest way that I would go through to explore a problem. And from that, you know what I mean, that's where my videos provide you like an aha. You're like, oh, I could do that. And then when you do that exploration, then that sets you down the path to figure out what the math is going to be. Because even on my last video, you know, someone kind of chimed in like, here is the mathematical equation, the relationship between something. But I think that's the circus trick. I don't think when people have a question about a problem that they can't do, they're not able to figure out just from an intuitive perspective what that math equation looks like. You know what I mean? Because those math equations are a combination of multiple things. And so when you get to a final answer, even an equation with variables, like, who knows, it's very difficult to actually tell where that stuff came from. You know, looking at an equation with variables, you can see, hey, these two things are a linear relationship. Increase one, the answer increases. Double one, the answer doubles. There might be an inverse relationship, or things to different powers. Okay, hell yeah. So let's begin. And yeah, I was going to say something. We'll see if I can remember it. But with projectile, here's the take-home point that can be very, very useful. It's that when you, let's say you drop something off of a cliff, it has 0 velocity. After 1 second, it has a velocity of 10. Now, the velocity is going to be what we call, you know, the acceleration of gravity. This is an acceleration. An acceleration, like the gravitational constant. An acceleration is a change in velocity, change in time. And because it's a constant, you know, it's going to be a, we can look at it like that. But because it is a constant, this equation definitely applies. Because it's, when you drop something, at any given time, it's going to change its velocity. So if we choose a time of 1 second, this is where this equation becomes change in velocity over a change in time of 1 second. Then, and we actually put a number to this, then every second we're going to have a change in velocity. You know what I mean? So that's where, and I think even from physics, you know, writing this change in velocity as velocity final minus velocity initial, I think some intuition gets lost there, just compared to, hey, we have this property that, you know, if something is near the Earth's surface, whether it's on Everest or, you know, at sea level, it's all about the same. You know, this number, it's not quite 10, you know, probably 9.8, 9.81, depending on if you're up way high, 9.79 maybe. You know, who knows how, you know, in a trench, maybe it's 9.82, don't know. But hell yeah, you know, 9.8, 9.81. But it's close enough to 10 that you can do some intuition with this that's really cool. You can just be like, hey, I'm going to drop a rock for 1 second, and then I know that its speed is 10 meters per second. The same thing is if I throw a rock or a baseball, you know, upward with an initial velocity of 10 meters per second, and then what's going to happen after a second? Its velocity is going to be 0 meters per second because it's going to change in velocity. So I'm allowing a time of 1 second to elapse, because of the force of gravity, it's going to reduce in velocity by 10 meters per second. And this kind of is trippy because we think, like, if I have a block of mass in space, and let's say it's just 1 kilogram, and it's got 0 velocity, and I want to accelerate it up to 1 meter per second. It's got a velocity of 0 meters per second, and then I'm going to accelerate it to 1 meter per second. I need to have applied a force. Oh, and let's say I apply a constant force. So I'm going to apply a force that's going to be constant. One way to look at this is you could look at this as like an infinitely long spring. The longer and longer you make the spring, and we got some tension in the spring, springs do have a force based on their length or their change in length from the initial position. But, some ways to visualize this, hey, this spring is so long that if it just moves a meter, it's applying the same force, and that force is going to be a constant. So that's a way to maybe look at a constant force. The same thing with, something falling. We have a force of gravity here, but because it's at a lower elevation, the force of gravity there is going to be different. We just say that it's insignificantly changed. And anytime I've mentioned this, I've mentioned that anytime that I use g, the gravitational acceleration, I'm always going to write Newton's law of gravitation, or the gravitational force equation, however you say that. But it's the gravitational constant, the mass that you're observing and analyzing, the mass of the Earth. And this system is the Earth, and then we have a cliff, and then, a chunk of mass. Maybe that's one kilogram of mass, and then here's the mass of the Earth. And just think 6 is, 6 times 10. This one's to the 24. And there's gimmicky ways that I use to remember this equation, but gravitational constant, the mass you're analyzing, the mass of the Earth. And all this is saying is that you have a huge chunk of mass here, you have a chunk of mass there, and we have this relationship that 2 chunks of mass want to move closer. And what we can do, and this is, I'm not going to go into it, but I need to get better and faster at this. I'm treating this as if the entire mass of the Earth is just right at the center. So I have 1 kilogram there. We have this pretend, radius of the Earth, but I'm just going to concentrate all the mass of the Earth right there. And now these two have an attraction. There's a huge distance between them. That distance is going to be the radius of the Earth, which we just call, kind of a generic radius. Doesn't matter if you're on Everest or in like a trench. Just for simplistic, because I've already said that this number for the force of, whoa, I gotta slow down. Well, what is this? Is this the force of gravity? Yeah, because we're also going to couple it with the force is equal to mass times acceleration. If I have a chunk of mass just in outer space or in its own universe, like if I'm kind of doing the God thing and I'm being like, hey, I'm going to have a universe with all the same properties that this universe has. I'm going to put the first chunk of mass in it. I want that mass has 0 velocity. I want in 1 second this chunk of mass to have a velocity of 1 meter per second. I have to impart a force, whatever that's going to be. And that's where we won't go into it, but yeah, what is a force? You know what I mean? Like you can ask the question why quite a bit. And even the force of gravity, I don't think it's fully understood. Einstein used this kind of, is that still kind of like the fundamental property is like the warping of space-time in like a cone where, if this is the Earth and then, this is the little chunk of mass on the surface of the Earth, that this thing's going to start rolling that way. Not quite sure. But anyway, so yeah, these two equations get coupled together. And then this is divided by the distance. Sometimes you could just put x squared. This is probably, you should do this actually more. But for this, we're going to say it's the radius of the Earth squared. you would put just a generic X as a position, because you don't know if this is Mars and then this is a cliff on Mars with the 1 kilogram. You know, because then the radius of Mars is just a distance. It's a distance between the center of mass of the planet and then the center of mass of the thing that you're dropping on the surface of that planet off a cliff. And usually planets are so large in radius that this height of this cliff is irrelevant and to the distance. And that's where, from a mathematical perspective, one way to explain that is if I'm adding, let's say the radius of the Earth is 6 times 10 to the 6. You know, it's what is it? Is it 6.6? No. But yeah, the radius of the Earth is just 6 times 10 to the 6. I think it's 6.03. Don't get me 037. Don't get me you know. But yeah, let's say I did guess right. I don't know if it's a 27 or a 37, but we have 6 million. So we have 6,037,000, and then we'll just make up it doesn't even matter. Let's say this is the radius of the Earth, and then and that's going to be, and then we're going to drop a and we're going to have something up 10 meters, and I want to know if the force of gravity is going to be different 10 meters lower, and so then we have this 6,003,7,010. But you know, like most, this is a physics thing. Typically, significant figures that you're going to be using are just in the ballpark of 3 significant figures. Like this doesn't really change the problem. If I put this, you know, because this is my radius, this would be the force of gravity before dropping it off the cliff, maybe right here at 10 meters higher. All right, hell yeah. So I'm glad I'm going over this because I think in the JEE mathematics sections, problems are like this, where if you have something where the significant figures are so minuscule, you can just like lop off huge parts of an equation, you know, and that kind of simplifies things. And you can do so, it almost feels like you're doing it in like a derivative sort of way, like taking the limit as something goes real small and this thing's no longer significant, or you approach an exact answer. And like one example of this is in material mechanics, where you're taking very specific equations that are complex, but then you're saying, hey, the distance things move is just so minuscule, and because of that, like the things like metal doesn't stretch very far, and you're treating it like a spring maybe, and then so you can simplify things. But then when you get a problem that involves not a chunk of steel but a rubber band, you know, it's still going to have the same properties. A rubber band is linear. It has a linear elastic range just as a chunk of steel does. But the equation that you set up that was based on small movements now does not apply to a rubber band. And so then you have to bring that equation back in. Same thing here. If I'm going to drop something from a height of 7 million meters above the Earth, you know, above the Earth's center, and it's going to fall to a height of, you know, sea level at 6 million meters, then the force of gravity is significant. You know, this being your leading significant figure changes by 1. Now, is there a term for that, like 1 point? You know what I mean? Kind of in, I don't know if is that a investment term when you're just like, hey, things increased by 1 point? I'll have to research that because I would like to use that more, because we're going to be talking about, you know, like this distance typically around the radius of the Earth, and if it goes from 6 million to 7 million, that should have a definition, like, hey, it definitionally increased by, I don't know, you know what I mean, because I think when you're talking about percentages, you can talk about 1 point, but not, you know, it's hard to tell if what am I saying? I have no idea. But yes, 6 to 7, 60 to 70, 600 to 700. Are these jumps similar? Like, it doesn't feel like it. It seems like, is there a way to figure out if those jumps are similar? No, I think as a fraction they're all the same. Yeah, so those feel like similar jumps. Anyway, all right, we got to move on. All right, hell yeah. But before we do, this is, I mean, if I'm going to pull out Newton's gravitational equation, you should have this one kind of down from memory, and even if you don't remember all parts of it, because we have the gravitational constant. I just think, the devil, 666, because it's 6.67, so close enough. And then just think a lot of sixes. We got 6 times 10. We got 666 right there, times 10 to some sort of exponent. We have, and then we have, okay, let's put this into this equation. So if I put the force of gravity into this equation, and we solve for the acceleration, I'm going to have gmme divided by the radius of the Earth squared. I'm going to have mass over here and acceleration. I can divide both sides by the mass, and those cancel, and I'm just left with acceleration. So the acceleration, which we call a very specific g, is going to be the gravitational constant, mass of the Earth, divided by the radius of the Earth squared. And if you kind of forgot what the mass of the Earth was, or the radius of the Earth, or the gravitational constant, this is my way to kind of explain it. 666. Now you can remember it's 6.67, whatever, times 10 to an exponent, and then the mass of the Earth is 6 times 10 to an exponent. The radius of the Earth is 6 times 10 to the 6, you know what I mean? So this one is 6 times 10 to the 6. This is like 6.0, like I said, is it 6 point, and yeah, I might even be wrong on this. Is it 6.37, that's where, I think this is like 6.37. But that's where, I'm just memorizing those. Well, I guess I'm memorizing the fact that it's 6. But that's more, that's, yes. I mean, that's a good one to memorize, that the Earth is 6 million meters. Okay, so hell yeah. And then we're going to square this. So this becomes 6 times 6, you're going to have 2 of those, and then you're going to have 10 to the 12. So that's downstairs. This 6 cancels that 6, this 6 cancels that 6, and what do we know about gravity? This is just 10 to the 1. So all of this has to add up to, this exponent plus this exponent minus 12 has to equal... minus 12 has to equal 1. Cool. And then so, if you can remember that the Earth is 6 times 10 to the 24, that's probably an easier one to remember. And maybe you forgot this, but negative 11. So this is 6.67 times 10 to the negative 11. Just think 666 times 10 to the negative 11. And then you're going to add negative 11 to 24. That's hard for me to do, but 24 minus 12 is 12. Minus, it's just a 13, so I have 13 minus this 12, and I get 1. So that's how this whole thing boils down to approximately 10, and that's why I went through this, because we're going, for this problem, the first thing we're going to do is just make an assumption that the force of gravity, on a chunk of mass that's in free fall, or a projectile, it has a force of, the force is this equation. Force is going to be the mass of that projectile times its acceleration. Its acceleration is what we found, and that is g, and that's going to be 10. So I need to get better about that. But yes, a projectile is going to have an acceleration or a change in velocity of 10. And we just showed that every second, the velocity of a projectile is going to change by 10 meters per second. Hell yeah. Okay, so now we can kind of start in on the actual problem at hand. Booyah. Alright, hell yeah. And I have looked at this problem. Last night I actually took a look at it. So, you know, that said, I haven't put anything to paper. I just thought of one way to start. But this says, let's read it. A particle gets projected from the ground, and then it passes 2 points, which are at a height of 12 meters, and then the second height is 18 meters and above the ground. And then there's a distance between these 2 points of 10 meters. Okay, so this is so fascinating to me because I'm going to do something that a student's not going to do right away. And it's just because they don't want to put in extra work, and they might think it's irrelevant. But it's totally not. I think this is the way I'm going to do it. I'm going to say that this distance is 0 meters. You know what I mean? And I'm going to say that the first point is at 12 meters. So we have 12 meters right there. And then the second point is at 18 meters. And then we have something that gets projected upwards. And then, I'm sorry, this doesn't have a question. The question for this problem is, what is the minimum velocity? What is the minimum velocity? Like when you project something, you're going to like fire it out of a cannon. Hell yeah. And then you impart an initial velocity. Then, like disregarding friction of air, then you make an assessment of what's going on. I think it's useful to first, I think this is the first thing that I like to do. Pretend like you created a universe with nothing in it, and you have a mass that's moving at 10 meters per second. This mass is just going to keep moving at 10 meters per second. So that's a Newtonian law. Like, I'm so bad at remembering what numbers of Newton's laws are which. But, hell yeah, that's a very important one. Okay, but now, we know that if this mass is right there, and we have this huge chunk of Earth, and then this scenario now becomes, you know, a chunk of mass, a cliff, and now the Earth is so large that this is the radius of the Earth, you know, and it has a chunk, and it has a center of mass down here. And so now what I like to do is you know, make that in outer space. Like, make an invisible Earth, you know, that has all of its mass centered just at that point. And then this is this is what you're creating. So you get to snap your fingers, create a new universe. You're going to throw a chunk of mass in it that maybe you're dropping off a cliff. I think that's the easiest thing to visualize compared to throwing it upward. And then you have a chunk of mass that's this distance away, radius of the Earth. And alright, hell yeah. And, okay, hell yeah. And I'm just going to add to switch batteries. But I think this is very useful because a lot comes up in free body diagrams, and like, I think that's tricky. It took me after graduating and then coming back to math and physics to be like, man, there's got to be a better way. Because even in the definition of free body diagrams, you have this word free, where it's, I don't know, you're kind of analyzing something like it is floating in outer space. Even if I have, you know, this chunk of mass resting on the ground, a free body diagram says, well, let's pretend like it's the only thing in the universe, and then put the forces, you know, because if it's, and then see what forces on Earth would be applying. Because the force on Earth, I mean, you do have an Earth underneath this thing, and it's actually pulling down. You have a force of gravity, and we know that because if that chunk of mass is you, hey, your feet hurt all day from standing, you know, from working and stuff. And so there must be a force pushing you down. But then we know from this Newtonian thing that if you did a free body diagram and you have a force, you know, pushing you down, so just any sort of force, and you're a mass, you should be moving in that direction. Because if you're the only thing in the universe and something is having a force on you, then you should be accelerating in that direction. The only, if your velocity is initially 0, after 1 second, your velocity, maybe it's 10 meters per second. Why does that not happen? It's the only way that doesn't happen is if there is another force pushing up, and then we have a net force of 0. So that's where the free body diagram, I think, gets explained poorly, or maybe I just, I don't know. I think a lot of time should be spent on the free body diagram. I have my method of just being like, hey, that thing that you're analyzing, pretend like it's the only thing in the universe, whether you snap your fingers and make a new universe to the side of, the actual universe that this mass you're taking it from, but then put a force on it that's observed in that universe. And then once you do that, once you identify at least one force, you're like, I know this is a mass, and then it is, this other mass of this planet is underneath it. There has to be a force based on the fact that this is just one of the biggest observations in Newtonian, discoveries. And then so when I go to my new universe, I'm putting that force on. Cool. And so I didn't have to know how there was two equal forces, but I just used this logic of like, no, I know that I'm putting this mass in a new universe, and there's some sort of force on it. And due to one of those other numbers of Newtonian, fundamental laws, I know that if I have a force on this mass, it's going to, move. I just use the word move, and then I always like to have an initial velocity of 0, just mentally, because you're like, okay, if it starts at rest and there's a force on it, it's going to now be moving. And it's accelerating. I think acceleration is a harder term to quantify, just because when things accelerate on Earth, they're going to go from 0 velocity to some velocity, but then for whatever reason, things kind of peter out. You'll go from 0 to, and you'll have something like this. This is basically all motion that we're familiar with on Earth, just due to friction and all sorts of stuff. But in a true acceleration, this thing would just be constantly increasing in speed. Alright, hell yeah. And then from a free body diagram, I like the idea of going back and forth. On Earth, what do we observe? Do we observe that this thing's moving at all? No. Okay, so in this example, when we set up our new universe, put a mass on it, put a force on it, we would expect motion. But if we're trying to mimic these two, well, then the only way to prevent this thing from moving is to put an opposite force right here. And we're going to call that, the normal force. Force normal, this is force gravity. So you could say this is, Fg, Fn, or just N for that force. Hell yeah. And, And this is where, the gravitational force is, if I take any little chunk of mass out here on the Earth, it's being attracted. There is an attraction from this mass to that mass. And even this 1 kilogram mass is, can be a conglomeration of tinier mass particles. Like, you have to take that into consideration, even each electron, each proton and neutron. The protons and neutrons of each atom are going to be where, your mass, the major part of your mass of any chunk of mass is going to be. Hell yeah, so each of those is going to have an attraction. But that's where I need to get better. And for some problems, it's kind of complex. If this is a sphere, and this is, and I wanted to find the distance and integrate, I don't know, actually that sounds really complex, even just like right now for me. But that's something where it's just like, hell yeah, that should be the next problem that I do. Heck yeah, because this comes up a lot where we just oversimplifies things and just, hey, we're just going to pretend like the entire mass of the Earth is at its center of mass. So this is the mass of the Earth. It's right there. That's where it's located. And then everything else is just kind of an imaginary, but that's where it is located. Alright, hell yeah. So now let's do a free body diagram of this. Okay, so we have the mass of the Earth. It's just going to be that point particle. We have this mass. It's going to be right there. Here's our free body diagram. This actually is occurring on Earth. Someone is dropping this chunk of mass off a cliff. We know it's got 0 velocity. We know it's going to increase in velocity. After a time of 1 second, it's going to have a velocity of about 10 meters per second. Hell yeah. So let's draw a free body diagram of that mass. I'm going to make it the only thing in the universe, but then I'm going to go back and forth. I'm going to say, oh, this is a chunk of mass. I know that it has a force on it, a force of gravity. I know that we have this relationship that force is equal to mass times acceleration. And oh yeah. And the force of gravity is gravitational constant, mass of the Earth divided by the radius of the Earth squared, which we just call, like all of those three terms is the mass of the Earth, gravitational constant, and radius of the Earth squared. That is the G. So that's where you get mg. But yeah, anytime that you're doing force of gravity is just mass times this gravitational acceleration, I would at least write it this way. You know, I'll continue writing it this way because that didn't just pop into my mind right away. Hell yeah. So now this is the force, you know, on this mass. And so so this is the generic equation. And this is, I think this is the craziest part of free body diagrams. I'm going to drop this mass. It is a mass. This is the relationship that if there is, so this is the mass. If there is a force on this mass, and this equation is going to be for net force. You know, it's kind of a vector equation. Where mass is also a vector, but it doesn't change. Okay, so it's a scalar. So if there's a force on this mass, we will see a change in velocity. We will see an acceleration. And this is going to be like a summation of forces, and this could be a summation of accelerations. So if I have a chunk of mass and I can identify one force on it, force 1, but then here's force 2, and then maybe here is force 3. I want to figure out, you know, the net force. So one's going this way, two of them are going this way, one's going that way. So, you know what I mean? If the net force is in this direction, then that's going to be the force net, and that's going to be that part of the equation. So we're analyzing a mass, we have a net force, and then we would see I don't know if you'd call this a net acceleration. But yeah, that's where even in this equation you can kind of do it in superposition. Would that be the word superposition? You could say, hey, this force is going to cause it to accelerate down. This force is also going to cause it to accelerate down, but this force is going to cause it to accelerate up, you know, and then so you're going to get an acceleration 1, an acceleration 3, an acceleration 2. You know, these are going to be down, down, and this is up, and maybe when you add these up, your net acceleration is down. Okay, hell yeah. Alright, so what I don't like is the fact that this force of gravity is just mg, where you have this, you're trying to identify a mass and its motion. That's F equals ma. There's the mass. And then maybe you identify that there's the mass of the Earth here, and this has a mass. Then we can know our first force, let's call it F1, is the force of gravity. And I can say the force of gravity boils down to this equation that's mg. But these two look so similar that you're just like, huh, you know what I mean? Like, where do I put this equation? Well, you put it in this side. This is the force of gravity. And even though it has a term that looks like acceleration, you know, it looks like it needs to be on that side, that's the only weird thing. That's where I think if you write this force of gravity as gravitational constant, mass of the Earth, radius of the Earth squared, or have this bottom part be x squared, just some generic distance between two masses. Because these two masses could be an electron and a proton, you know, and the force of attraction between an electron and a proton. Hell yeah, and the distance between the electrons and protons. Yeah, so if I write it like this, I don't know, does this look, and I'm trying to figure out the forces on the mass, does this look like now I plug it into this side? You know, I'm gonna, if this equation is force 1 plus force 2 plus all the forces that are acting on this mass, and then once we do that, we could figure out what the acceleration is. Because forces add like vectors, you know what I mean? So if, yeah. And because of that, because they add like vectors, I have to analyze this and, you know, I have to give them vector components. So if I'm doing this problem in 2D where we have a height and then a distance this way, you know, then I have to take that into consideration. With falling objects that are changing with forces in this direction, all the forces are in this direction. On this, there's going to be no force sideways, and so I can analyze this acceleration just in this vertical direction, and I can just call that the acceleration of it. Alright, hell yeah, let's do it. So on this, the free body diagram is going to be right there. I'm going to identify a force of gravity. We have a mass, that's the only force on this. Doesn't look like any force is pushing up on it. We're going to neglect air. And so let's use our Newton equation of force is equal to mass times acceleration. I need to get better at the actual, like, do I put vectors here? Do I put summation signs? Like, what's the, you know, because I'm overly simplifying in that, and that's a detriment. But anyway, what I want to find is the acceleration. So even right now, you could either keep this equation as is, or say acceleration is going to be force divided by the mass, and maybe put the summation sign there, and the acceleration is going to be the force of gravity divided by the mass, and what was the force of gravity for gravitational attraction? Gravitational constant, the mass that we're analyzing, mass of the Earth, divided by the radius of the Earth squared. We're also going to divide it by this mass. I'll just put it right there. That's also the mass we're analyzing. Those cancel, and we can see that the acceleration of this is just gravitational constant, mass of the Earth, divided by the radius of the Earth squared. And this is where I just wasn't taught in college to look at a solution as, you know what I mean, as like, what are the variables? That means that this change in velocity has nothing to do, it's not a function of the mass. If I double the mass, I'm going to see the same acceleration. I'm going to witness the same speed. So this is why you can drop two things of different masses and they're going to hit the ground at the same time, because it's not a function of the mass that you're dropping. It is a function of what planet you're on and the mass of that planet. It is a function of the height from the center of that planet, whether you're on a tall tower above that planet or even, you know, in a space. Alright, hell yeah. So we got a new battery, and we were just talking about how the change in velocity of this dropped mass off a cliff is going to be a function of the mass of the planet it's going to be on, and then the height above. So you could be at the surface of the planet dropping off a cliff, or you could be in a spacecraft above that planet, and then you still just kind of drop it. And let's say you're in a hovering spacecraft, just to make, you know, it's still a one-dimensional problem. Cool. And then this gravitational constant. This needs to be explained way more, because, you know what I mean? Let's say it takes 2 apples to make 1 apple pie. Hell yeah. So apples are not pies, and pies are not apples. But we can come up with a simple equation that if I have 2 apples, or maybe I want to know how many pies, so I have a y is equal to x equation, and I say these like y is equal to something something x, and this is basically every equation. is I'm comparing things that are different. Because if I just say 1 is 1, cool, there's, I don't know, I mean, it's just an identity. 2 is 2. But we have equations where we can say, well, if I have, I don't know where I'm going with this, but, you know, this is pies, and then this is apples. So I want, and you know, this is really obvious. You know, if I have 100 apples, I can make 50 pies. But how do we put this into equation? I say that y, if this is 1, if this is 1 pie, this side has to be 2. Cool. So if I have 2 apples on this side, so I would say if I had 2 apples, the number 2, I get 1 pie. But now this says if I have 1 is equal to 2. I mean, I kind of know what I'm talking about. I know that this is pies and this is apples. But if I input the number 2 in this side, you know, it feels like I just have that number 2. But then, so if I input the number 2, I'm outputting the number 1. You know what I mean? So what do I need to do to this 2 to make it 1? I need to half it. You know, so I'm just going to multiply it by a half. And this is where, you know, just in a generic sense, we put a constant right here, k, you know, and then we have, so we have y is equal to kx. Y is equal to kx. Where the k is 1/2. So I have y is equal to 1/2 x. And now is this my equation? You know what I mean? And all we did there is this is a proportionality constant. And we can even make it make sense to say that if I have 2 apples, well, yeah. So let's actually, this is kind of fascinating to me. I don't do this one. I've never done this one, but that's why we do these. Because the other thing that we have here in this is I have 1 pie is equal to 2 apples. So I have 2 different things that are not equal. I have the number 2 is not equal to the number 1. I have apples is not equal to pies. So, so you know, these, even though I know that there's a relationship and it just makes sense, what I can do is this. I can do 1 pie is 2 apples. I'm going to take those 2 apples and I'm going to, you know, divide it by a half. And I'm going to say divide by 2 apples and then multiply by 1 pie. So then just from, and I don't know if this is just making me happy or something, you know, I don't know if it's mathematically sound, but this is what the constant of, the proportionality constant would be, because I need to cancel out these apples, and then I'm left with pies, the 2 cancels the 2, and I'm left with 1. So here, the proportionality constant k would be 1/2, or I would say 0.5 pi per apples. And hell yeah. So now I have an equation, y is equal to kx, where this, so now if I input, so the proportionality constant is 0.5 pi per apples, and then x, let's say I do have 2 apples, so I have 2 apples, the units on apples cancels, 0.5 and 2 become 1, and I get 1 pie. That's all that's happening, is I'm just comparing 2 things. If I have 2 apples, I know I can make one pie. You know what I mean? If I have 12 inches, I know that's 1 foot. And so, and those are 2 dimensionally similar things. They're 2 lengths. But even here, this equation says that if I have a mass in kilograms, a distance, and we're going to square it, that's all we have here. Is that right? You know, that's it. Then what we're going to achieve is something that's an acceleration, which is a meters per second per second. It's going to be a change in velocity, change in time. You know, kilograms is not meters or seconds. meters squared is not just this 1 meter. And then so we need a proportionality constant to, cancel the units as well as give us the appropriate number. And that's all that is. So this, even though this equation seems complex, it is still a y equals kx equation. Y is the acceleration, k is the gravitational constant, and the x is just a couple things, you know what I mean? It's just mass of the Earth divided by the radius of the Earth squared. That could just be lumped in potentially as just a simple, So even this could be seen as a y is equal to kx equation. Alright, hell yeah, that was probably a dumb thing to say because we just said that the radius of the Earth squared, and obviously it's downstairs and it's squared, so that makes it an inverse square. And so if I increase this radius, what does that do to this number? And this is where, we can take things to the extreme. If this is extremely large underneath a fraction, then the fraction gets really small. So if the radius gets huge, and now I'm dropping this mass off a cliff where that Earth is way far away, then the change in velocity is going to be low. And it's, it's a square. So if I double that distance, this change in velocity now quarters. So always have that in your mind when it comes to squares. And then when you double something, just as a relationship. If it's linear, if I doubled the distance, I would potentially, and if this was linear and this was upstairs, you know what I mean, and double the radius of the Earth, then the change in velocity would double. It's downstairs, so double the radius of the Earth, the change in velocity reduces by half, but it's squared. So double the radius of the Earth and drop something off, the change in velocity will be not a half, it'll be a quarter. And so that's what that square does. Alright, hell yeah. Alright, hell yeah. So now we can take it to our problem, because I'm going to show, hey, this is a fairly in-depth equation where what happens is that maybe you just have an equation like this, that acceleration is change in velocity, change in time. And for free-falling stuff, we're going to say this is constant. And so this equation does apply. It would be like the average acceleration. This is the average acceleration, but we're also saying the average acceleration is equal to the actual instantaneous acceleration, where instantaneous acceleration is a derivative, and we don't really even need to get too much into that, just because it's so useful to know that acceleration due to a free-falling object, gravity, because that radius of the Earth, that distance doesn't change significant enough, and we're going to call gravity 10 anyway. So the acceleration is going to be 10 meters per second. And I like to write it like this instead of like this. A lot of people write it 10 meters per second squared. You can graduate without realizing that this is a horrible way to write this, because it's not intuitive and it doesn't explain anything. It doesn't explain that you're going to have a change of 10 meters per second of your velocity every 1 second. Even if this isn't constant, if this is rapidly changing, that after a tenth of a second, like this thing is 20 meters per second squared, like this is the new acceleration, it's still more intuitive to be like, hey, at this initial time of dropping, time 0, had I dropped it for a second, it's going to increase in speed by 10 meters per second, and but then if this is the equation that after a tenth of a second, it's going to be 20 meters, and I just ran this thing for a 1 second, then I'm going to have 10 of those. And so my new acceleration is going to be 10. Oh, if it's going to increase by 10 times 10 times 10. So yeah, so after a second, my new acceleration is 100 meters per second. So if I just guesstimated that at time 0, the change in velocity was going to be 10 meters per second for a second. And I think after a second it's going to be going 10 meters per second, but now the acceleration is 100 meters per second squared, which I'm going to say is 100 meters per second every second, a change in velocity of 100 meters per second every change in time of 1 second. I'm going to run this for another second, and I'm going to have a speed of 110. And I'm fine with that. This is where you can get good and intuitive about physics, being fine with this. Even though like something in your brain's being like, no, this is horribly wrong, right? Because if I ran this for a tenth of a second, 1/10 of a second, I'm already, I'm going to be this speed. But that's where, hey, my change in velocity is 10 meters per second per 1 second. If I only run this for a tenth of a second, I'm going to have a speed of 1 meter per second. But after that 1 meter per second, now my acceleration is 20 meters per second per second. I'm going to run that for another tenth of a second. Not a full second, but just a tenth of a second. So now my speed increases by 2. So I went from 1 and then plus 2. So now I'm at 3 meters per second. Right here, my speed is going to be 30 meters per second. And so then I'm going to, and this is time 0, time 0.1, time 0.2. At time 0.3, I'm going to add another 3. So I'm going to be at 6. And let's run this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Because this was my initial guess after 1 full second. So this is time in tenths of a second, and this is 1 second. This is the distance, no, this is the speed, the velocity is going to be 1, and then I'm going to have plus 2, is that right? So initially it's going to be 0, then 1, and then 3. So I'm going to add this number kind of. So 1 plus 2 is 3. 3 plus 3 is 6. 6 plus 4 is 10. 10 plus 5 is 15. 15 plus 6 is 21. Plus 7 is 28. Plus 8 is 36. Plus 9 is 45. Plus 10 is 55. And so, and I feel like, Yeah. This I ran for 2 seconds. I ran this for 1 full second, and then this was for 2 seconds. So let's continue on. 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9, and then 2.0. And I can kind of slow it down because this is actually pretty interesting and useful. But after 1 second, my speed is actually 55. But still, this is still just a guess. It seems like now this is the right answer. But we can actually do this change in time of 0.01 seconds. So now after 0.01 seconds, I'm going to move the decimal place 2. My speed is 0.1. After another 0.01 seconds, now my acceleration is isn't 20, but it's 2, so it's 12 meters per second. So now move the decimal place 2, so now my speed is 0.22. And so now we're approaching, and hopefully I'm saying that right. But hell yeah. And then you'd be approaching a closer and correct answer. So this answer after a second of going 10 meters per second was the worst, and 55 meters per second was better. And then at 2 seconds, we were thinking we were going 110. And let's see, what are we adding? So this was 45 plus 10. This is 55 plus 11. That's going to be 66. And let's just use this. 66 plus 12 is 78. Plus 1.3 is 78 plus 13 is 91. Plus 14 is 105, plus 15, plus 16. So we got 120, 136, plus 17, plus 18, plus 19, plus 20. And so we have a speed of 210 meters per second. So basically double our initial guess. And this is still not the true right answer. Alright, so what we just showed was when acceleration varies, You know what I mean? We still want to get into the mindset of like, hey, running it for a second. You know, always, and even if a second gives you a terrible answer, at least a step in the right direction. You know, you can always make your improvements later. But even just to keep it simple in your head, I do like to look at the units of acceleration as a change in, that's what we were looking at. Even if this changes considerably and quickly, I still want to look at this as a change in velocity after running the thing for 1 second. Cool. It just happens to be that because the distance, because that gravitational, g is going to be gme, radius of the Earth squared, and this term hardly changes. Mass of the Earth doesn't change. Gravitational is a constant. This is just going to be, 9.8, 9.81, and we're going to round it to 10. All right, hell yeah. Cool, and it's a constant. So, and this is an equation. This equation says that we're going to have a change in velocity. So, if we say g is 10 meters per second, I like to say the units are the equation. Like right there is the equation. We can put a 1 here. We can put a change in velocity of, a change in time of, and we have this acceleration, which is g, is a change in velocity, change in time. And we can see that this is for average acceleration, but because acceleration doesn't change, this is also for, and we see that average acceleration is not instantaneous acceleration. If we use this equation to find the velocity at one point, at time 0 and then time 1, that doesn't mean the acceleration was constant during that second. You might have, the acceleration might have increased. But with free fall, it's always going to be constant acceleration. Cool. So this A for the acceleration at any given time, acceleration as a function of time, can be just this equation, delta V, delta T, which is velocity final minus velocity initial, time final minus time initial. I like to just think of it as a change in velocity, change in time. I think even thinking of it like this is, I think it's more complex and just kind of adds more. It seems like it's just adding variables that can confuse kind of the nature of projectile problems. All right, hell yeah. Okay, so we're gonna play around with this. So the two things that we're gonna play around with are the fact that here's the ground, here's 12, and here's 18. Here's here's height 1, here's height 2. They're just imaginary points in space. We could consider them maybe towers or something. And then the first thing I'm gonna do is throw a ball upward. Part of the problem is let's minimize the initial velocity. So if I just threw this ball upward, I could throw it and it could get way up there with a considerable velocity, velocity initial being quite large, and it's going to pass this point and it's going to pass that point. So it meets the requirements of our problem. It passed the 2 points, height 1 and height 2, but it did not minimize the initial velocity. Sorry I didn't write out this full problem. I couldn't really find it, so I just wrote it myself. And we want to minimize this. So how do we minimize it? What we want is the ball to stop. If the ball has, 0 velocity right at point 2, just barely gets there, then that's going to take the minimal amount of initial velocity. If the initial velocity was any less, the ball would not reach point 2, and we would not have it passing both points. Okay, so that's the first problem that we should do. And let's just try to do it from an intuition perspective. And we can even change these heights to make the problem easier. Okay, so I'm just going to pick an initial, and let's just pick an initial velocity. Let's pick an initial velocity of 10 meters per second. And that's the initial velocity of the ball. What do we know that's going to happen after a time of 1 second? The ball is going to have an initial velocity of 0 meters per second. It's going to come to a stop, and then it's going to fall back to Earth under that same influence of gravity, and it's still going to accelerate the same. Just because we have an a velocity this way, and let's say this is positive velocity upward, it becomes 0. Well, it's going to become negative, and that's going to be a seamless, if we're on a number line, and this is 10 meters per second, and this is negative 10 meters per second, and this is 0. After 1 second, the ball is going from this speed to this speed, and then after another second, the ball is now going this speed. And because this change in velocity is uniform and linear, if I took the time is equal to 0.5 seconds, I would be, so if this is 1 second, and what do we, holy Toledo. So the initial time is 0 here, and we're going to throw it upwards. It's going to slow down, so at time is equal to 1 second, it's going to have 0 velocity, and then time is equal to 2 seconds, it's going to hit the Earth again at the same speed that we threw it. It's just in the opposite direction. It's going to hit the Earth. So I could have time of 1.5, time of 0.5. It's still going up, but it's going slower, 5 meters per second. At time of 1.5, it's coming down, but it's coming down at 1.5 meters per second. Now here is, if this is your first rodeo with these problems, what you're going to find is that these velocities seem very useful, but they're not. It's not 100% intuitive of how to figure out the height of the ball. Off first glance, it might be like, well, isn't it halfway? The ball's halfway up, and we're going to try to tackle that one right now. All right, hell yeah. And so the next thing I'm going to talk about also is so fundamental to calculus, because calculus for differential equations, like solving differential equations and integrating, I think it's the fundamental theorem of calculus. You know what I mean? I hate those terms because it doesn't, but it should just be the continuity. Anyway, it's based on this. So let's say your acceleration is like a curve like that. And it's, here it's almost, let's say this is 0. We're at almost 0 acceleration, and we're almost like time, let's say this is time of 0 to time of 1 second. At time of 0.5 seconds, we don't have any acceleration. The change in velocity is going to be low, so we're going to see this particle maybe not moving. But then all of a sudden, up here we have a very high acceleration, like change in velocity, and what I should say is, let's say this is a velocity diagram. So let's say this is just velocity. We don't have any velocity. We have hardly little velocity. And then all of a sudden we have like 10 meters per second. And so now the question is, like, what is, like how far did it go? And in this case, we would simplify it, be like, well, let's just say it didn't move at all. And then here, we're going to do this. And so this is what calculus does. It's going to take something that looks like a curve and then, just chop it up. And basically what it says is that if we take any 2 points that are very close together, it looks like they're connected by a straight line. If we zoomed in on that, we would literally maybe see this. And maybe I drew that too straight, but maybe we would actually just see, like, that. But it would be so close to being straight. And then if we did the same thing, if this is the actual line, I'm going to pick those 2 points. And those 2 points, for sure, are going to even look like a more straight line. But maybe they're not. And then so that's what they look like. And then I'm going to pick 2 more points. So that's that's the deal, is that even if you have something that's highly sharply curved somewhere, like where the curve is the greatest, if I take 2 points that aren't too far apart and kind of zoom in on that, it looks like that is just a straight line. And we can analyze that little section as, a straight line, and then it's kind of easy just to be like, well, isn't there an average? So I'm just going to take that value. That value is going to be, if this is the velocity of 10, and this is 20, maybe the average velocity is 15 meters per second for this time interval. And so hell yes, that's what we're going to do. So when I throw a ball up at 10 meters per second and a second later it has a velocity of 0, I mean, the first thing that should pop into my mind is like, well, does that, if this is velocity and this is time, does that look like this? 10 to 0 over 1 second, and this is 10 to 0. Does it look like that, or does it, I mean, does the velocity just drop off rapidly and then just kind of slow to a stop? Like, you know what I mean? And no, it doesn't do that for free fall. So that is the most useful thing for projectile problems, is that you have constant change in velocity. This is it's a linear relationship. And so if I wanted to, yeah, and I think this is non-intuitive, because if I say a town is 60 miles away, and I drive 60 miles per hour, how long does it take to get to that town? And then you have, let's say, another town that's 120 miles away, and you drive 60 miles per hour. And then another town that's just 30 miles away, and you're driving 60 miles per hour. At 60 miles per hour, driving 60 miles is going to take 1 hour. I think that's very intuitive. Driving, if you had to double that distance, 60 miles per hour for 120 miles, is going to take 2 hours. This is going to take half an hour. But now here's the scenario that I think, I mean, I don't know. I think it almost needs to be proven, and maybe I just take this for granted. From this scenario, let's say you had a town. Well, let's do this, 30 miles, because you could maybe do this, maybe. You could have a 30-mile chunk of road maybe no one's on, and you could slowly increase your speed from 0 to 60 miles per hour. So if this is your velocity graph over this distance, this is what you're going to be doing. So over that distance, you're going to reach a final speed of 60, crossing that finish line. Now the question is, what's your average speed? It's just going to be right in the middle. The average speed is going to be 30 miles per hour for that trip. I think something about that problem, like I feel like I would want to need to prove that mathematically, but I'm okay with just saying that's the case. And so, because that's what we're going to have to use for a lot of these physics problems, is you'll have, something with a speed here of 10 and a speed there of 0. The average speed is 5. So for that interval of 1 second, the average speed is 5 meters per second. That means that, even though we were going real fast at the start, real slow at the end, it's like we threw this ball up with a speed of 5 meters per second, and it ended with a speed of 5 meters per second. 5 meters per second. And so in that scenario, if a ball is just constantly moving at 5 meters per second for 1 second, how far did it move? You could use the units or the equation. We have a speed of meters per second. We have a time of 1 second. What do we do to these to get the distance? Distance is already on top. I'm going to multiply, seconds cancel. And so I'm going to take 5 times 1, and it went 5 meters. So in this problem where we throw a ball up, I've just picked a speed of 10 meters per second. It's going to have an average speed of 5 in 1 second. It's going to go 5 meters, and it's going to stop. Okay, so that problem only going to go 5 meters. Ours says that we have to go 12 meters and 18. We have to get up to 18 meters. So let's just play around with the numbers and start increasing this. So I'm going to have an initial velocity of 20 meters per second. So now I'm glad I did this, because this is where it should just be intuitive. This thing is going to go from 20 to 0. At some point it's going to stop. How long is that going to take? So after a second it's going to go from 20 to 10. After another second it's going to go 10 to 0. So maybe I should put that in here. So initial speed of 20 meters per second. After a second, I don't know where that's going to be, maybe up here. Because if I'm going to try to draw this to scale, it's going fast at the start and then slow at the end. So I'm going to be here at 10 meters per second. and then here is 0 meters per second. This is 0 time, this is 1 second, this is 2 seconds. So if I figured out what the average velocity in between this is, it's going to be 15 meters per second for a second. The average velocity here is 5 meters per second per that second. And so I went 15 meters and then 5 meters. So I went a total of 20 meters. Now, could I have done this just saying that the, my speed goes from 20 to 10 over 2 seconds? Sure, if it went from 20 to 20 meters to 0 over 2 seconds, the average speed is going to be 10 meters per second. And then the time that would have that average speed would be 2 seconds. And so we have 20 meters per second. I'm sorry I went fast through there, but and I probably should have slowed down, but that's why we did just all of that kind of slow lead up to get to somewhere intuitive so you can just kind of snap that out. And that's why we are choosing our own numbers. Like this is why we're using a guess and check thing, because I just said if I have an initial speed of 20, I can get up to 20 meters. And this thing's at 18. So hell yeah. So right now we even have our first initial guess that the velocity is, I don't know, somewhere close to 20 meters per second. And I think that's important because we might be getting a technical equation for this problem. And if we're wrong on one of the technicalities of that equation, it might give us, something like 2 meters per second or 200 meters per second. And then we might realize we're off by a factor of 10, and that would be, kind of a red flag. All right, hell yeah. All right, hell yeah. Okay, so now we're kind of getting into the good part, is that these two are going to be at, 2 distances apart. You know what I mean? So I think, I don't know, we just came up with a scenario where after 2 seconds, with an initial velocity of 20 meters per second, this thing can get to a height of 20. So let's change this to 20 meters. Cool. And so that's going to be the first thing that we do, like make your own problem, because that can simplify things. And then what we're going to do is we're going to have this be projected up at an angle where, and then we have to kind of know this, that, the velocity initial at some sort of angle is a vector, and it can have 2 components. It's going to have a velocity in the y initial and a velocity in the x initial, depending on what kind of angle we give it. And the entire vector is just the velocity initial. This is, and it would have, something in the I hat direction plus something in the j hat direction. And this would be the x, and this would be the y direction. Cool. If we have an initial velocity of 20, then it's going to get to a final height of 20 meters per second. If we give it an initial speed this way, let's just give it an initial speed of 1 meter per second. That's the simplest thing that we can do. And, I don't know, just because it's, a base unit. We know that this thing is going to reach the top of its arc, or just the top elevation, after 2 seconds, because we have that acceleration of gravity. A or g is going to be 10 meters per second every second. So a change in velocity of 10 every change in time of 1 second. Okay, so in 2 seconds, and this is the other thing about the free body diagram. If we have this thing and we have an initial velocity, v initial, in the x direction of 1 meter per second, the only thing that's going to, and this is a chunk of mass, and a free body diagram says, hey, let's take this, thing and put it into its own little universe, but then come back to Earth and then say, hey, is there any forces on it? Well, in this direction, in this x direction, there is no forces. We're neglecting air resistance, and there is, what I like to, I don't know if it's a fun thing to say, but just, hey, there is no Earth over here. You don't have a huge chunk of mass over here that's pulling it that way. I don't know, maybe the sun rose in the distance, and yes, you do have the sun rising just right on the horizon, and that is a gravitational force in the x direction. but it's we're going to neglect it because it's so small based on what we said, the significant figures. I mean, by the time that actually changes the velocity, it would be very small, 0 point whatever change in velocity. Okay, so there you go. So we don't have any forces, and so we have F equals ma in the x direction, no forces in the x direction. We do have a mass. If we rearrange this equation, the acceleration in the x direction is force in the x direction divided by the mass. The forces are 0, the acceleration is 0. So we just have no change in velocity. So this velocity is going to start at 1 meters per second, and it's always going to be 1 meters per second. So after 2 seconds, so then our average velocity in the x direction is just 1 meter per second. It never changes. And so when this thing gets to a height up here after 2 seconds, we already went in this direction 2 seconds. So we have 2 seconds in the x direction at an average speed of 1 meter per second. So in the x direction, we move 2 meters. So if this second point is 2 meters right there, this is 1 meter, this is 1 meter. If that second point is right there, and we had this setup, we would just reach it, and then we would be coming back down on the same parabolic arc. So now let's figure out when would we actually get to, and let's say this is just 10 meters, make it simple. If that is at 10 meters, or maybe this is the time that we could, because 10 isn't going to be a very useful, well, let's try 10 and then we'll throw in 12. So if this is at 10 meters, oh yeah, I think this is kind of tricky. You're just like, at what time are we actually going to reach this point? And at what distance this way? Because alright, hell yeah. So what I'm in the process of doing right now is kind of deriving the equation for the position. And I'll say the position is the position in the y direction. And when I want position as a function of time. And, cool. And so, if this point is at 10, so if I have an initial speed of 20 meters per second, so I think I'm going to be in a process of working like forward and backwards to try to get this equation. Cool, yeah, so let's run it forward, and we're going to run it for just 1 second, because we know 2 seconds is going to get us to this height. I kind of want to know where time is equal to 1 second. Like, what height is that going to give us? So that's the question. Like, what height is going to be time is equal to 1 second? So after 1 second, my speed goes from 20 to 10. I'm going to have an average speed of 15 meters per second. Average speed is 15 during that 1 second, so I have a height of 15 meters. So now, like right here, I need to figure out what I did. I had an input of 20. I had, I figured out that after 1 second, I had this. And then that gave me, and then I used an equation to get the average velocity. Once I knew the average velocity, I multiplied this by that time. You know what I mean? And then I got the position. And so I just chose 1 second. Let's say, and that got me a height of 15. You know what I mean? But so right now I could even just use a guess and check. I could choose a time of 0.75 seconds. And let's do that for the first one. So I'm going to say in 0.75, I'm going to go from 20 meters per second and we know that every second my speed is going to decrease by 10 meters per second. What happens in a half a second? In 0.5 seconds, my speed would decrease 5 meters per second. So in 0.75 seconds, my speed is going to decrease 7.5 meters per second. So I'm going to go from 20 minus 7.5 meters per second. Shouldn't that just be 12.5? But 20 minus 7.5. And so I'm going to have a speed of 12.5 meters per second. I'm going to have an average speed, and then let's figure out what the equation for average speed is. I'm going to take, and I need to save the juice on that, I'm going to take 20 meters per second plus 12.5 meters per second and then divide by 2. So that's kind of how you find the average between any two numbers. Let's say I wanted to find the average between 1, 2, 3, 4, 5, let's see. Let's say I wanted to find the average between 1 and 5. The average is going to be 3, you know what I mean? How could I get that? Well, I'm going to take 5 plus 1 and then take the halfway, and then half that, find the halfway point. So it's kind of, you know, just the way to find the average between two numbers. Cool. So I'm going to have 32.5 divided by 2. That's going to be 16.25. All right, let me just double check. Okay, so we have an average speed of 16.25. That's going to be our average speed. But we're only traveling that average speed for 0.75 seconds. So again, this is our speed, this is our seconds, the units are the equation, and we're going to multiply these two together to get our distance. So we're going to multiply 16.25 times 0.75, and we're going to get a height of 12.1875. So that's actually, that works out perfect, and let's just say that's what we wanted. This height I wanted at 12.1875. This height I wanted at 20 meters. Cool. And now where, and I'm just going to put this first point at a distance that makes sense, you know, because my initial speed is going to be 20 meters per second up. I'm going to have an initial speed 1 meter per second over. I just chose those arbitrarily. And it's going to pass the first point at 0.75 seconds. On the way up, it's going to pass this first point at 12.1875 meters at a time of 1.75 seconds. Hell yeah, that's right? Yeah, I think so. Let's see. Oh yeah, because in 1 second, it was 20 meters per second, 10, average speed of 15. So yeah, after 1 second, I was already 15 meters up. I only had 5 more meters to go. And after that second, I went another 5 meters. And so, cool. Alright, hell yeah. So if that took 0.75 seconds, and I had a speed this way of 1 meter per second. Again, the units are the equation. I have 1 meter per second. I have 0.75 seconds. The units on these are going to, when I multiply, the seconds cancel. I'm going to be left with distance. So this is going to be at a distance this way of 0.75 meters. And we said this took 2 seconds to reach the top, and that was going to be 2 meters over. So the distance between these 2 points in the scenario that we just did here is 1.25 meters. So we at least did a simple problem that gave us an initial velocity, you know, some sort of up component and over component. That can give us the angle as well. And then we know that it's going to hit point 1 and 2. If point 1 is at 12.18 and then point 2 is at 20 meters high. And the distance between those is going to be 1.25 meters. So then for this problem, our initial velocity, the minimum, or yeah, I don't know if it's maximized or minimized. Alright, hell yeah. Okay, so now we're getting into the juice of the problem, because this problem is kind of like a minimization problem. So it fits in the category of like maximizing or minimizing something. And I think it can be difficult, especially when you get like a picture that looks symmetric. You're just like, well, doesn't this, like if the problem stated this was height 1, this was height 2, and the distance between them was 1.25, it seems like the fact that this projectile, like ball or whatever, comes to a dead stop at the top, it seems like that's minimizing this initial velocity. And then so, it's even hard for me to see, like, well, how could we change this problem? And so, yeah, so let's redraw it. And so we have the ground. I'm going to kind of draw it in kind of the same way that we did it. And what, did we say it was 0.75? Yeah, so this was 2 meters. And so at 0.75, this is where we hit. This was going to be 12.8, what, 875? No, 12.1875, basically about 12 meters. And this was going to be a height of 20 meters. So we did change the problem around. We were able to find that this distance between these was 1.25 meters. So now even for this problem, if this was the problem I was given, and we found one solution, we have an initial component of 20 meters up, and an initial component of 1 meter per second over. This is where I think it'll make sense if we give the actual initial velocity. Because just because we have a 20 meters up and a 1 meter over, this initial velocity is going to be using Pythagorean's theorem, 120, and so this is going to be 20 squared plus 1 squared, and that's going to be like 2 squared. And then this is 20. I like to do this, especially if you're not using calculators. 20 is just 2 times 10, and then we're going to square that. The square can be applied to the 2, it can be applied to the 10, plus 1 squared is just 1. And so we have 100 times 4. So we have 400. Even though, like, I should be able to just see that this is 400, I don't know, maybe I messed up and said it was 4,000. So this is the square root of 401. The square root of 400 is very close to 20, and so yeah, we just have a small variation. So we have the square root of 401, and this velocity is going to be 20.0249 whatever meters per second. Now the question is, can we reduce this and still hit both these points? You know what I mean? Both points have to be at these elevations. And if this is our starting position where we're going to launch the projectile, at the origin, the thing that can vary is the distance that these 2 points can be over. And so, yeah, okay. So, yeah, so like even, this is hard to see, especially since we chose like a very steep angle. But let's say, this is my initial velocity. Let's say I just shot this straight up with this initial velocity. Well then, I'm going to, because this is the initial velocity straight up, the change in velocity, it needs to be, it's going to go from this to 0. And so that's going to be the change in velocity. The time it takes to do that, and let's use an equation. Acceleration is 10 meters per second per second. That's going to be the change in velocity, change in time. So here's the equation that I have, and that's the equation that I said. It was acceleration is change in velocity, change in time, and this is the actual instantaneous acceleration, and I can solve for it using any average, any velocity components, velocity final minus velocity initial. Just making sure I have the times on them, time final minus time initial. And so I know that this is going to change in velocity from 20 point whatever to 0, and maybe I don't know the change in time on that. Okay, but I do know the acceleration is going to be 10. So let's rearrange this equation for change in time. I think this is one of the hiccups that I always run into, is that you have these differential equations, and you even have a solution to this. Is the solution to this differential equation, just because acceleration is constant. And if you do have, I feel like sometimes these seem like not equations, but this is a solution to this equation, and we can rearrange it any way we want. So I can solve for change in velocity. That's going to be change in velocity is acceleration, change in time. I can solve for change in time. Change in time is going to be change in velocity divided by acceleration. And so that's kind of what we're going to do. Because we would have, I'm going to store, calculator's dangerously low on juice. I'm going to store this value as x. And that's going to be my change in velocity. I'm going to divide it by 10. Cool, this is my change in time. It's 2.00249. I'm going to store that as alpha t. Yeah, I'm trying to figure out, whoa, yeah, this is the hardest part for me. Of like, hey, we're just going to change something, and we're going to see if we can get an improvement. But it's hard to tell. Alright, I'm going to try to watch. This is the hardest part, and I don't mind taking my time. This is kind of the first time going through this. If I used this as my initial velocity and I shot this thing straight up, I would pass through these 2 points, and I would be, getting too high. There'd be no reason to get that high. But the distance between these 2 points would be 0. That d would be 0 meters. And if the problem stated that it had to be 1.25, we have to keep that. And then so let's see what I could do. What I could do is I can, so because this velocity that I did for the initial problem, this is what we're trying to compare to. I'm trying to reduce this, but let's say I just reduce it just a little bit, 20.002. So I reduced it by this 49, those units. And now this is the overall velocity that I can put into 2 components. And so the idea is, let's increase this, so this is 20 point, and if this is the overall, let's say this is 20.015. Cool. And it just happens to be that this component is 0.5 meters per second. Or let's just say I don't know. I increase this one. Yeah, let's talk about this just if this is 20 and this is 1, and these things add up to this number, which I want to reduce. But this number I want to be greater than 20. That's what I'm trying to figure out. So this number is going to be 20.015. Let's just see what this number would be by an equation. So if Pythagorean's theorem said that this number I want to be 20.02, which is reduced, this component is going to be 20.015. What is this? And this is one from Pythagorean's theorem. Typically, you're going to add these. You're going to take this, square it, take this, square it, add them, and then take the square root. If you're given the hypotenuse and one of the sides, you're going to take the hypotenuse squared, and then you're going to subtract it from one of the sides squared. So you can go through the math on that, but I think it's just intuitive to know that it looks similar to the Pythagorean theorem of a squared plus b squared is equal to c squared. But when we're given the hypotenuse and a side, it's the hypotenuse squared minus, let's say, b squared. And this gives us a squared. And if we take the square root of it, this gives us a. So that's what we're given. That's what we're trying to find. So we got square root of 20.02 squared minus 20.015 squared. And I feel like, did I do that right? Yes, this is a smaller side. And then, so that means, and we were pretty close on 0.5 meters. So cool. So just from this, our speed this way is going to be 0.4474 meters per second. And, this is probably a huge overshot. And so what we should have done is just reduce this by maybe... Alright, sorry about that. We got a new battery in. And, okay, so one aspect is I don't know how this is going to change the problem up. You know what I mean? Because obviously this is going to change how far these things are spaced this way. Dramatically, actually. So I can just tell that this distance is going to shrink substantially. Yeah. But what is going to happen is that we increased this speed. So now the projectile, if I accentuate this, is going to have less of a component that way. Is going to come up, let's say here, is going to pass this 20 meters because it has a higher component in that direction, and then it's going to start to come back down. Okay, so if it does that, this problem says it just has to pass through the 2 points. It doesn't say that, I think this problem is, I don't know, you know, it probably stated that, you know, it passes through point 1 right there, and it can pass through point 2. It can pass through point 2 twice. Oh, no, never mind. I'm sorry. This second point is not just a horizontal line. You know, it's not just a height you're reaching. This second point can be right there. So that's what we would have. In this scenario, because we steepened our angle with a higher velocity, we're going to go higher than 20 meters. And then on the way back down, we're hoping that when we reach point 2 at that height, this distance is still 1.25. But just from intuition, this speed is so low that that's probably not the case. So now, I think the hardest thing, especially when, you know, just doing problems in this way of just like, hey, let's just guess, is like right now, how do we use this, you know, how do we use our new information? Because we're saying that we have a component up of 20.015. We have a component this way. I'm going to store that as the x. Well, no. We'll just store it as w. So this will be w. And this component is going to be 0.447409. Hell yeah, and that's going to be stored as w in my calculator. Cool. So now let's go through the process, and, you know, I mean, we're just going through the process intuitively, but that's where even when we figured out this height, we kind of just guessed, and then we were just like, okay, we're satisfied with that. So, yeah, so that's probably going to be the biggest hiccup for this video, is to maybe even right now slow it down and get an equation for these heights, cool, based on these initial inputs. And it's just the kinematic equations. I'm just going through, I like to do projectile problems just from like an intuition instead of using the kinematic equations. I think the second you just write the kinematic equations, a lot gets lost. And then I'm even going to double down and saying if you use calculus, like a calculus approach of the acceleration equations to find velocity and position, I still think a lot of intuition gets lost. Hell yeah. Alright, I'm trying my hardest not to just use the calculus and then set up equations and then find variables and unknowns and then solve for them. I really do want to use these inputs and kind of figure out, well, if I use these inputs, I know I'm going to reach this point 2, because I know I'm going to get up to 20 meters, and on the way back down I'm going to get 20 meters. I just know that this distance, you know, the difference between this distance in the x direction and this point 1 in the x direction for sure isn't going to be 1.25. That is going to get drastically changed. Now for the problem, what we would do is just change this ever so slightly. So I would reduce I would increase the vertical component very, very, just ever so slightly. And did I even get that right? No, yeah. So I said this was my initial velocity. It was the components of 20 and 1, and I got this. What I wanted to do is see if I could reduce this initial velocity to any other number. So, I just took this 9 away. That was chill. But now this is my overall velocity. So then I took this overall velocity, and I still wanted this upward component to be just slightly less, but I could have just done... I could have reduced this number by this, 20.0248. No, I'm fine with what I did. I could have, yeah, I'm fine with what I did. But I could have reduced this to 20.019. If I did that instead of 1.5, let's do that. Just to see if that gives us a different or better answer. So we got the square root of 20.02. Yeah, we're happy with that. Subtract. I'm going to say that this number is 20.019 squared, which is slightly less, and then that pops out. Oh, no. That makes this. Oh, I see. Yeah, that makes this worse. So I need this to be close to 20. So I'm going to go 20.005. There we go. So we got the square root of 20.02 squared minus 20.005 squared. Because this is just slightly greater than 20, so I know it's going to go up and over this range and then hit on the way down. When that happens... hell yeah, now this is going to be 0.7748 meters per second. And then so what I'm hoping for is that a steeper, well, I don't know. What am I hoping for? I reduce my velocity. I'm able to get higher than 20 and then come back down. And so... yeah, and I'm just hoping that this, gets farther that way. It doesn't look like it's going to. Not from this perspective. So that's interesting. Now I'm curious is if there's a minimum distance that once you if these two things are, very close together, that... the minimum velocity is hitting this point on the way up. But if these two things are very far apart, we could kind of play around with that. If you have something like at a 45-degree angle and that's your arc. And this is your distance, 12 on the way up. But then on the way down, you're reaching, let's say, this point right there. And then this distance is going to be maximized. And so that's going to be that 10 meters. I could see that being the solution just from an intuition perspective. Alright, and hell yeah, now let's talk about why. Because if I had to hit this point on the way up right there, look at that. If I said that, look at this, because look at the difference. Look at the difference in elevation. There's not too much difference between this point in elevation and this point in elevation, but there's a huge distance this way. Because if I put this point, this second point, at the top right here, we'll call it 2 prime, then this distance gets significantly reduced, Well, and 2 prime would be right here. So I could shallow my trajectory, and get to there. But then let's take a look at what happens. So I could shallow the trajectory, and if we're coming in shallow, we're going to finish shallow. Point 1 is going to be right there. So here's my new point 1. So here's 1 prime, and here's my new point 2 prime. So what we see is this point 1 moves this direction, not very much. But point 2 So the initial point 1 and 2 were right there, with a significant distance between them. If we shallow the angle, you can see that this distance gets hella reduced. So if this was my initial problem of just being like, hey, let's hit up here, then this, and we're calling this, so this was the initial distance that we were trying to find for our problem. But we can see, just a second. I'm trying to see if in both of these problems the initial velocity would be the same. Is that being represented with this picture? Alright, hell yeah. So I'm going to redo this picture, but I think we're on a good route. And I'm going to introduce the fact that it's just known in physics that a 45-degree angle when you shoot a projectile is going to get you the farthest distance. So if I shoot a projectile at that angle with an initial velocity. Now if I slacken the angle but shoot it at the same initial velocity, what happens is that it doesn't go as far. So here is where it's going to land. It's not going to land out there. That's the max distance at 45. If it's shallow and it's the same angle, it's going to land there. And so, here is that new so here's the midpoint of that. And it's not going to go as high. And that's kind of the idea of why it's not going to go as far, because it's not up in the air as long. So if I'm shooting a shallow angle with that same speed, it doesn't get up as high, and it comes back. And so both these are the same speed. This is just the perfect angle at 45. This is shallow, but both of those same initial speed. And then so here's the midpoint on that. And so my picture, and here's the midpoint on that. And so if this was where point 2 was, and then we just come down just somewhere arbitrary, just past midpoint, and this is where point 1 is. On this one at 45, point 1 is going to hit right there, and then point 2 could be way out there. So that's where this distance, is kind of, it feels hella maximized when this is 45. Yeah, that's kind of interesting. Not that. Yeah, I'm trying to figure out if it's just 45-degree angle is what you want always to get the. I don't think so, but maybe. No, let's yeah. If I'm having a hunch on that, let's draw some of these diagrams, because if I say this is perfectly 45, and then that's going to be the farthest arc. So that's where I'm going to get if I'm a 45. We said if we went shallow, so I'll just do one that's hella shallow, and then so we're going to get to the halfway point. So if I go super shallow, same initial velocity. Now I'm going to do one that's super tall. If I go super tall, maybe I land right there as well. And then so, I get height up to there, but I just don't get the actual distance. And then let's put our distances on here. So if I say this point at max is going to be, or where did I put this? Well, and I could change these up. So here it would be 0.2 maybe, and then, no, because at the shallow, I wouldn't be able to hit 0.2 at all. So we're going to put 0.2 right here, and then 0.1 right there. And the graph got a little bit messy. We can do, and then we'll just disregard that line. Okay, so on the ideal, here's 0.2, and then where's 0.1 on the ideal scenario? 0.1 is right here. So that's the distance between 1 and 2. On the shallow scenario, we barely get up to 0.2, and we cross 0.1 right there. So that's and all triple star this. This is the other. On this steep scenario, 0.1 can be right there, and then 0.2 could be right there. So hey, like is that... So that's the distance between the steep scenario, but this is the distance between the ideal scenario. So the ideal scenario still looks... So given the same initial velocity and you choosing the angles, trying to get the distance between 2 points. Alright, so my intuition says that's not true at all. Just because we have the scenario of shooting something straight up, where if I shoot, if here's 0.1 and here's 0.2, and I kind of shoot these straight up, it seems like I would want to just barely hit 0.2 on the way down. You know, just get up to 0.2 and have it stop. So that seemed intuitive from the first setup. It didn't, you know, it seemed tricky to actually steepen this, you know, trajectory and then have it, you know, go up a little bit higher and then come down at that same distance. So if I steepen the trajectory, 0.1 prime, you know, goes this way, and then so it shifts that way, and then 0.2, you know, also will shift that way. We're just hoping it doesn't shift that way as much, you know. And that sentence might not even be true. Alright, hell yeah. So this is the part of the videos that I kind of want to spend the most time on, is kind of learning in front of the camera. Because I think it's a hell of a good skill. So we're not going to put 0.1 and 2 on yet, but we are going to do the 45-degree trajectory, and then we're going to do the shallow and steep. So kind of the halfway point for the shallow, and then maybe we're going to get a little bit higher. Yes, you get higher but not farther. So we're going to do that. And now if 0.1 and 2 are... yeah, I'm just trying to think. Yeah, and let's maybe do a card in here. So let's say that's 0.2, and this is 0.1. And maybe we're just going to look at these two lines right here. So the distance here is obviously greater because we have a shallow trajectory. But what are we trying to change? Oh, yeah. Because the other thing that we're trying to look at is, I mean, the distance between 0.1 and 0.2 right here, this has a greater distance. But the distance between 0.1 and maybe on the way down, 0.2, compared to 0.1 and 0.2, this still feels like it's a greater distance. Is there any point where yeah, if I'm right at the top here, which is maybe somewhere right there, this steeper arc is over there. So there's a chance that, there you go, so 0.2 can only, almost. Alright, I had a huge sneeze. Glad I didn't capture that on camera. Let's see. So here's the 45-degree arc. point 2, let's say it's just right at the top. And point 1 is going to be on the up. Then the distance between point 1 and point 2, just kind of measure this out, is going to be right there. The distance between point 1, for the steeper arc, the distance between point 1 and where point 2 comes down, and I don't think they're too much difference, but it's just right there and there, well then that's going to be better. That's going to be bigger. Because I see now. So this 45 starts and finishes the greatest distance. But the midpoint is, the midpoint is going to be halfway. But if you do a steeper angle, I can get this direction of the midpoint from a steeper angle. I think that's what I'm learning from this. And so this is good. If I use a steeper angle, I can get this direction of that midpoint. And that means that I'm actually starting this direction of where point 1 would hit. So a 45-degree arc, which gives you the best length trajectory this way. If the problem says, hey, I need to hit point 1 and point 2, and on my 45-degree arc, I'm hitting point 2 right at the top of its arc, right there. And that distance, I'm trying to have be 10 meters. So that's what we have. Let's see. Let's get a new card. So that distance right there is what I'm going to call 10 meters. With the same velocity, we're saying, hey, this is the same velocity. It's going to be steeper and then, kind of land shorter, but it is going to go steeper. That just visually is going to have a higher or a longer distance. For that same velocity input, maybe we get 14 meters. That means that we can shoot at a steeper angle. So I can reduce this velocity to where I can still have the steeper angle. It's still probably going to what happens when this arc has this angle but gets reduced in intensity? I'm going to start along the tangent line, but I'm not going to go as high. I'm going to deviate from height, and then I'm also going to deviate from length. And so the center point is not going to be in the center. The center point is going to shift. So I'm going to deviate in height. I'm going to deviate. The highest point is going to be offset that way. And then I'm going to come down, closer to there. Okay. And then what I want to figure out is if that is approaching. So let's get, this is going to be our point 1. That's what we said was point 1 because we have, well, let's get this. So here was our initial right there. And so all right, we switched batteries and we're back at it. And so I just wanted to put these in here. So if that's 10 meters, that's going to be point 1. And then so I can bring up that as the line for point 1. That's the height of point 1, and yeah, cool. And what we did is we had this be the steeper angle with the same velocity, and then what we did was we reduced the velocity, and we got a distance of 14. It's too great. We can reduce the velocity. That's the whole problem. We can reduce the velocity and still get this distance to be 10. And so with the reduced velocity, this shifts in. And let's go back to and where are we saying is point 2? Yeah, right at the top. Yeah, so point 2 is just kind of this line all the way. So that's point 2. From this initial arc, we're going to say on the way up. Oh, it hits right there. and then it comes back, and then it hits point 2 right there. So that's where we had that 14. Now, if we reduce that, we're going to take a shallower trajectory, and so this is where we got. We're going to hit point 2 right there, and then we're going to hit point 1 on the way up, just a little bit closer. Well, hardly any difference. Okay, hell yeah. So we're going to take that up. Hell yeah, and look at that. So now we're basically just right about there. So we kind of figured it out that we were able to reduce our velocity with a steeper angle, and we're able to get that down to 10 meters. And so that is enough proof for me that the solution potentially isn't going to be a 45, is because we can do a steeper angle and get through 2 points. Yeah. I still think it's kind of hard to explain. If we did that 45-degree angle and we hit point 2 right at the top of the arc, we're going to get the max, distance this way we could ever get. And we could take that same velocity and steepen it, and then come through that point. And what is that what we showed? Because if this is point 1 and this is point 2, we see that this is 10 meters. So we're only getting a distance of 10 meters between those 2 points. But if we take that same velocity and steepen it, we're shifting this quite a bit this way. And then when we come down with that, let's say this was what we were trying to show, this initial one. We can come down. So we're starting on this side of that point 1, and then we can even end, yeah, that's fascinating. We can even start to come down and be on that side of point 2. That's why I had these arrows. So we're going to be on this side of point 1, and then that side of point 2. So that happens. And I think from a visual perspective, I think I'm pretty settled with that. Alright, hell yeah. Before this problem just runs away from me, and I actually want to do it, I want to go back and try to use the actual inputs that they have. So I'm just going to do kind of a generic 12, 18. I think that we want a steeper angle. We're going to come up and then come down. Cool. And on the way up and then on the way down, this is point 1 and 2. So now I think this is going to give us that distance of 10 meters, and it's going to give us the lowest velocity input. Alright, hell yeah. And I think the hardest thing to do is what we just did in the beginning, is just try to guess. We tried 1 meter per second and we hardly got any distance. So let's try, and we know this thing might be up for about 2 seconds. You know what I mean? So it's going to be up for 2, and so I don't know. Our distance this way is 10. So maybe we have an average speed of 5. So let's do 20 and 5. 20 meters up, 20 meters per second up, 5 meters per second over. Now that's a total guess. And then let's try to get equations for trying to hit these points. So if we're 20 meters per second up, let's figure out the equation it takes to get to 12 meters, this point 1. And let's just run it for a second. So I'm going to guess. So this is where I'm going to guess a time of 1 second. I know that's wrong. So from right now I know that's wrong. But then I can adjust that time and then maybe get an equation for the time that it takes. So this 20 goes from 20 meters to 10 meters, this vertical component, with an average speed of 15. Cool. And so right there I took the initial velocity and then I subtracted the acceleration. And then you have to figure out, is the acceleration this way? Is the acceleration, like what are we calling positive? I'm going to call this the positive direction, and the acceleration of gravity going to be negative 10 meters per second. So it's going to slow it down. So I'm going to take my initial velocity, which is positive 20, and then I'm going to add it to the acceleration times the change in time. That's what I did there. But I think that's very hard to see. But from an intuitive perspective, what did we do? I said this 20 meters per second was my initial velocity. I use this term like run it for a second. We know that under the acceleration of gravity, due to the forces on whatever mass, and it's irrelevant of the size of the mass. Cool, we're going to see an acceleration on that projectile of 10 meters per second. So if it's got to speed up, away from the center of the Earth, it's going to slow down by 10 meters per second in that second. So after 1 second, it's going to be going 10 meters per second. And so the velocity after 1 second is equal to the initial velocity plus, what did we just do? I took this 20 meters per second and then I subtracted 10 meters per second. How was I able to do that? Because acceleration is negative 10 meters per second per 1 second. And I said I ran it for 1 second. So that's, and then you're basically taking this acceleration times time. Negative 10 meters per second per 1 second times 1 second. The units cancel, and I'm left with a change in velocity. So my velocity after 1 second, which you could consider velocity final, but like I said, I don't mind velocity initial, but the velocity final, I think it gets, you lose intuition maybe when seeing just this velocity final. Instead of just saying, hey, the velocity after 1 second, initial velocity plus that acceleration, could be considered g, it doesn't change, times the time. So that we have the 20 meters per second plus negative 10 meters per second per 1 second times 1 second. Units cancel. 20 minus 10. Our velocity after a second is now 10 meters per second. And then we use that knowledge to be like, well, can I make the simple assumption that the average velocity during that time frame is just 20 plus 10 divided by 2? And yes, you can, because the change in velocity is linear. Cool. And then that gets down to calculus. We said that if you have equations that are not linear, you can break them up into small chunks, and you can consider that chunk to be linear. It's not, but if this chunk is fairly small, it's accurate enough. Even this, you might only have to divvy up into 3 chunks, even 2 chunks, 4 chunks, and you're just got a really good approximation. These are just all linear chunks, and you're using that same equation on each of these chunks. The average point right there is just this plus that divided by 2. It just happens when acceleration is constant that this is always accurate. Cool. All right, hell yeah. And this is challenging me for just being like, hey, you know how to do this, and what I'm doing is I'm relating intuition with the kinetic equations, which is super important. Cool. And I just chose the 1 second, but if we figure out what the equation is, it's this. So there you go. And then once we found that velocity final, which was that? This was the velocity final. Cool. So now we have velocity initial plus velocity final divided by 2 gives us the average velocity. What are we going to do with that information? This is 15 meters per second. Now I want to find the distance that it traveled, in this y direction, because it had an average velocity up over 1 second of 15 meters per second. I'm going to take, you know, those meters per second, I'm going to multiply by second. The units are the equation, seconds cancel. So I'm going to take that average velocity and multiply it by that time, and that's going to give me my height, you know, in the y direction. And so let's do that. So 15 meters per second times that time of 1 second that we ran it, quote unquote, that's going to give me a distance of 15 meters. Now, is 15 meters greater than 12? Hell yeah. So our time is going to be less than 1 second. You know, and so that's why you do these initial guesses. So when you actually run the equation, you're not going to be surprised. You would be surprised if you got 1.25, made a mistake. You know what I mean? 0.8. Hey, probably the right answer. So now what I like to do, and it's difficult for me, is to do this process in reverse and see what we did. The average velocity right there. So to get this distance, this is what we were striving for. I needed to find the average velocity and multiply it by time. The average velocity was the velocity initial plus the velocity final divided by 2. So that goes right there. The velocity final was the velocity initial plus acceleration of t. That's why these equations, especially the kinematic equations, you know, don't mean much when you actually just plug everything in. So let's plug this into there, and then that into there, and then kind of simplify it. So we have velocity initial plus, and this velocity final is velocity initial plus acceleration times time. Then we have divided by 2. And you can see that, oh, I have 2 velocities right here. Cool. And then this is 1/2 AT. You know, we could do that right now. But, so I took this velocity final, plugged it into there. This is the average velocity. I'm taking this average velocity and plugging it into here. Now I just multiply by time, and I'm given this y. This is the distance in the y direction. And so this is 2vi plus AT divided by 2 times t is equal to y. This is going to be vi plus 1/2 AT, all times t is equal to y. And so this is vi t plus 1/2 AT squared is equal to y. And this is our kinematic equation. And depending on how you want to write it, I don't know, I would rather write the acceleration out front. So I would say the position in the y direction is 1/2 the acceleration times squared plus velocity initial times time. Just because this is your, when you do the integration method, this becomes like your constant of integration. You know, do you have an initial velocity? Yes. If you didn't have an initial velocity, it still applies. You just maybe dropped it off a cliff. No initial velocity, but now you have an acceleration. All right, cool. So we have a kinematic equation. But like literally my mind now goes blank again. You know what I mean? Because this is too much. It's too hard to mentalize those 3 components into this one succinct equation. And so like you lost all intuition. But from this, now we can find the time. And we see that, it's like a square root equation where, I mean, we could just use a guess and check, but even if we did do a guess and check of just changing the time, why are we going to get 2 answers? Because we're trying to find where this thing hits height 1, but it's going to hit height 1 on the way up, and then it's going to hit height 1 on the way down. I mean, so we could have an intuition for that to be like, hey, on the way up, like, you know what I mean, my velocity, we ran it for a second. My final velocity is still upward, you know, and then we figured out the height it was going to be, and that height was 15 meters. It's too high off the ground, so obviously that time is going to be a little bit less. And so we could just do a guess and check to get that time value. Cool. But now that we have the kinematic equation, I don't know, you know what I mean? I'm going to solve this from, you know, if we have ax squared plus b bx plus c Holy hell. Is that the... It's been... Oh, I've taken a break from this stuff. Is that a polynomial? Is that a quadratic polynomial? It looks like it. Is that quadratic polynomial have the solution x is equal to negative b plus or minus the square root of b squared, because it's underneath the square root, minus 4ac, because there's a lot of negatives, and then divided by 2a. And yeah, it's negative, a lot of negatives, right? The whole thing's just... That's a good way to remember it. You got a negative, negative. You just got negatives everywhere. The only positive is just right there. And then let's double check that. And so one way to double check it is divide everything by a. I like to do this. So we have x squared, and then get this to the other side. So we have x squared b divided by ax is equal to negative c divided by a. And then we got to complete the square. We're going to get an x plus something, and this something, this term right here is going to be half of that. So it's going to be b over 2a. And when we do that, you know what I mean, because we're going to have this times that when we, you know, and then we're going to have this times that again, and that's going to be that term. We're going to have this squared, that's going to be that term, and then we're going to have this squared, which we don't have. So we have to add it to both sides to make this, you know, the completed square. So we're going to add b squared divided by 4a squared over there, and then we're going to take the square root of it. That's going to be the plus or minus, and then we can then now subtract this b divided by 2a. That's how I do it in the simplest amount of steps, and we have x is equal to this. Now how do you get this to look like that? Well, you say, hey, let's put another 4 top and bottom, and let's put another a squared and then an a up there. So this is your negative 4ac. We can switch these, so we got b squared minus 4ac, if you see that. You know, this square root, you know, this, we can do the square root of the top and then the square root of the bottom. That's square root of 4, square root of a squared. And when we add these fractions, you can just have 1. And then obviously this is just 2a. We have a 2a there and a 2a there, so that's going to be all over 2a. And then we have, you know, just this negative b. So, and then what you would do is you'd put the negative b out front, so you get negative b plus or minus the square root of b squared minus 4ac divided by 2a. But that is the way I do it, you know, and I just follow like the logic, you know what I mean? It makes sense to do the math in that order. It makes sense to complete the square and get this, you know, and just right away, whatever I did right there that gives you the answer the fastest. You completed the square, you solve for x, you got a square root, and then obviously you're going to subtract this on the other side, you know, instead of subtracting it and then adding it to all that jazz. Anyway, alright, so yes, we know what a quadratic is. Alright, so let's use it on this kinematic equation. So we need to solve for t. We have, and I'm just going to change this a to g because that's what we have. And then so this is my a term. This is my b term. And for this one, yeah, we just don't have any c term because my initial position, that's what it would be. Your initial position would be, you know, starting at 0 meters. And how did that not pop out? I guess I knew I was going to start at 0 meters. I knew I had an initial velocity, so that was already known. So that's where, you know what I mean, my height right here is just a function of the average velocity times the time. But else this component would be the initial height plus average velocity times time. And then if you did that, then this equation just has a plus y initial. And I'm sorry, that's probably going to be, I don't know. If you do this from acceleration, you know, this is your first constant of integration, and then this is your second constant of integration. I should say this VI, this velocity initial, is your first constant of integration. Your second constant integration is this YI, not this VI times t. But anyway, I shouldn't even be saying that because I'm just avoiding the calculus just to try to show intuition of how these kinematic equations kind of work out. But now we're at the point we have an equation we're going to solve for t, and we don't want to use guess and check. So I'm going to say t is going to be this negative b component. And where's our, b is vi. So we're going to have negative vi, and that's it. Yep. Plus or minus the square root of vi squared, minus 4. Our a component is 1/2 g. So I'm just going to go 2g. Hopefully I'm okay with doing that. C is 0. Oh. Yeah, so that term just drops. Our C value is 0. Okay, hell yeah. And then so we have negative VI. So we have negative VI plus or minus VI. So this is either going to be negative 2 VI or it's going to be 0. Oh man. I feel like no, okay. My bad. So this is the equation for the height based on a function of time based on the initial position. The initial height is 0. Cool. We figured that out a while ago. But this is still part of the quadratic equation. The height that we're trying to find is 12 meters. And then so our quadratic equation, we got to get this to the other side, is now going to be 1/2 g t squared plus vi minus the height final, which is y final. That's going to be that. And if I do it just with straight letters, now this is equal to 0. This is my a term, this is my b term, this is my c term. And so if we have negative b plus or minus the square root of b squared minus 4ac divided by 2a. And there's so many places to make errors. Anyway, so we have negative vi is my b term plus or minus the square root of the b term squared, vi squared, minus, I'll just do 4, a is 1/2 g, and then the c term is a negative y final, and so this is going to be an addition. So this is going to be plus 2g y final. Hell yep. And that's going to be all squared, so v initial squared. So that's what we have, plus or minus negative vi. All divided by 2 times our a term, which is 1/2 g. So this is just divided by g. Okay, and this is our time. Hell yeah. And let's plug it in. Our initial velocity we're just choosing is 20. So we're going to have negative 20 plus or minus square root of 20 squared. That's going to be 400 plus 2 times negative 10. So we do have a negative here. And then a height of 12. All right. And then divided by g, which is negative 10. All right, so let's throw that in. Let's see if we can do this. So we have negative 20. We'll do the plus first, square root of 400. I'm just going to do the minus 2 times 10 times 12. Hell yeah. All divided by negative 10. Yeah, this is an all divided by. So many places to make errors on the Pythagorean theorem. That's why I don't like it. But hell yeah. We got a time of 0.735, and now we kind of double checked it off that 1. We thought it was going to be close to 0.8, and so we're good on that. So I'm pretty satisfied that that's it. I'm going to store that as alpha t. Okay, so cool. And again, we're just using a guess and check. We just put an upward component and an over component, and now we're going to figure out when it hits this 18 meters. It's going to hit the 18 meters in 2 different locations. It's going to hit the 18 meters on the way up and on the way down. But we are trying to, we don't want this distance to be 10. We want, we're trying to maximize things. So this full distance, should be 10 meters. Oh, but yeah, we can kind of slow it down. And I guess this is where the problem is getting into the math and, you know what I mean. So we found our time. That's going to be our time. We gave this an initial velocity of 5 meters per second. So I'm going to take that time times 5. And because if this is 5 meters per second times that time of 0.735 seconds, seconds cancel. And this is the distance this direction that point 1 is. So point 1, I'm going to store as alpha A, is going to be 3.675 meters. Cool. Now what we're going to do is figure out the time it takes to get to this height of 18. And that's going to happen twice. So we're going to have to use the same Pythagorean's theorem. So we're going to take this y equation. Y was, what was it equal to? 1/2 at squared plus v initial t. Get this to the other side, and we have a quadratic that says 1/2 gt squared plus vit minus the height that we want, which is y initial. And we broke that down to this equation right here, which so the time it takes to get there, it's going to hit this 18 meters at 2 different time frames. And so we're gonna use the velocity initial as negative 20 plus or minus the square root. This is 20, so it's 400 plus 2g. That's going to be negative 20, and then this y final is going to be 18. So we're going to have 18 right there, and then we're going to all divide it by negative 10. So just back to this equation. And we're going to have a positive root and a negative root. I put in the positive one first. So we have negative 2 times 10 times 18. All right, hell yeah. So that's going to be 1.36 seconds. We'll do this negative root, and it's 2.6 seconds. So we have a time of 2.632 seconds. I'm going to store that as alpha s. And then I'm going to multiply it by 5, so times 5. And then I'm going to store that as alpha b. So this point is going to be at 13.16. And hey, we've already guessed fairly good. You know what I mean? We're going to take alpha b minus alpha a. And hey, we set up the problem pretty succinct. And this distance is going to be 9.486. Hell yeah. So one way that we could adjust, our values is just increase this, by 5.1 meters per second. And so, hell yeah, we could even do that like right now to get, because we know what this time to point 1 is, and we know the time to point 2 based on a trajectory upward of 20 meters per second. That's completely irrelevant of the distance it travels this way. Cool. And then so we're going to and what do? We take, and then we just choose this velocity. So we have the velocity in the x direction initial times this time 1 is this distance, 2.1. So that's going to be, I don't know, maybe you call it x1. And then we have velocity initial in the x direction times time 2. And that's going to be x2. And then so the distance between these, d of 10 meters, is going to be the difference between them. So d, which is equal to... Alright, hell yeah. Switch batteries out, and we're going to show that the difference between these two is the distance. And we want that to be 10, and we know what t1 is, and we know what t2 is, and both involve the velocity initial. So we have, x2 minus x1, which is velocity initial in the x direction, t2 minus velocity initial in the x direction, t1. We can factor out that velocity x initial in the x direction, and we have t2 minus t1. Hell yeah, and that's that distance. What we're trying to find is this initial velocity, and so we're just going to take this and divide by that d. So we have d divided by t2 minus t1, and that's going to give us our initial velocity. This distance we want to have 10 meters, And then so alpha s is t2, so and then alpha t is t1. So alpha s minus alpha t, 10 divided by that. So 10 divided by that answer. And so our velocity initial is going to be 5.27. I'm going to store that as alpha v in my calculator. Okay, so now what we want to do is try to see if we can improve these numbers. And this is where, I think from just changing a parameter, that's what we're trying to find. I'm going to change one parameter, just a very small change, and I'm hoping the output gives me, something that's better. Cool. And then for this one, I think it's almost crucial to keep, I don't know, like how I would do this is if I chose 20 meters per second and then I chose this velocity now that we found was 5.7 meters per second in the x direction. I know my overall, using Pythagorean's theorem, this is how vectors add. We're going to have 20 in that direction, 5 in this, and I should have drawn it. That's going to be our vector total. We're going to have 5 that way, 5.27 that way, 20 that way. Cool. And this is v, and this is 20. So this initial velocity is going to be equal to the square root. It's just going to be 20 squared plus v squared, square root of that. So that's what we have, and we have 20 squared plus alpha v squared, square root that. I'm going to store that as u. So u is going to be my initial velocity total. And cool. And I'm going to use that throughout the problem, but I am going to change one thing. The parameter I'm going to change is this angle. And so I'm going to figure out what this angle is. So I'm going to use the inverse tangent of, because what's tangent? Tangent of this angle is the opposite over adjacent. It's going to be 20 divided by 5.27. So if I take the inverse tangent of both sides, this gives me the angle is equal to the inverse tangent of that. So I'm going to go inverse tangent 20 divided by 5.27. I'm going to check if I'm in degrees. Cool. So this gives me an angle of 75.238 degrees. Okay, hell yeah. So I think I don't know. I really want to just change this by a 1 degree. But I don't know. Sometimes in maximizing and minimization problems, your first guess, if you're able to do it with a calculator, you might want to just change this very little. So what I'm going to do is increase this. I'm fine with that. I'm going to just add 1. I'm going to store this as theta, and then I'm going to increase the angle to theta plus 1 degree. So that's going to be 76.238. If I increase that angle, then and I keep this velocity initial the same, then these two parameters change. And so let's find those two new parameters. Cool. That's what we're basically doing. And so I know my initial velocity is u, so I know this is u, but I know my angle changed, and then so I need to figure out what this is. So I would say that, I would say, hey, this side is, this side would be the sine, so I would say sine of this angle is equal to the opposite. That's what I'm trying to find, and that's going to be the velocity initial in the y direction divided by u, just my overall initial velocity, the total vector. And then I'm going to say cosine of theta is going to be the velocity initial in the x direction divided by u. Cool. And I can say that, hey, this velocity in it is just bring u upstairs in both of those. So yeah, that's it. And if we think of this being the total vector, its components are related to this angle. Like the sine component is the percentage of this, like the hypotenuse, the larger. Yeah, so if I take this larger number and multiply it by a percentage, that's going to give me this component. That's going to give me the component. And so this percentage is the sine, because, sun is shining on the sine component, the other component's the adjacent. Cool, it's the cosine. But it's always, if this is the cosine, if I know the cosine of this angle, that's going to be whatever this hypotenuse is, the larger number, it's going to be the percentage. I'm going to multiply that. And I think of it as a percentage. You can think of it as like a fraction of a whole, because the cosine of an angle is a number between 0 and 1. That's, like 0.5. That's more of a fraction of a whole. But you can see that 0.5 is 50% of this. And even, I'm trying to get used to also, yeah, cool. So this is about 20. Always divvy this in half. Hey, look at that. Well, I didn't draw this to scale, but if I did, this looks like it's about the same, like 10, and this looks like it's about, fairly similar to this, fairly close to 20. But I did not draw this to scale. All right, so let's get our values. Our new values is going to be alpha u, sorry. So it's alpha u sine theta plus 1. So we're going to do the theta plus 1, which is the 76. And I'm going to store that as alpha d. So this becomes alpha d, and then I'm going to do alpha u cosine. And I'm going to store that as alpha e. So this becomes alpha e. Okay, so I have 20.09 basically, and then 4.92. So those are my two components. And then there's my resultant, and that's going to be u. So now we're just going to run the whole scenario, like, and then see if we could actually chisel this down. Yeah. I guess this is the time-consuming part, because we're just like, bummer. Yeah, we have new inputs, and then we want to see if, the goal is to see if the distance changed. Like, I'm now just going to use this as my new velocity, in that x direction, but I'm going to see if this distance changed. So this distance equation is x2 minus x1. I know my velocity in the x direction. I need to find my time 1 and my time 2. So yeah, that's Pythagorean's theorem, and that's going to be this equation. So my time 1 is going to be negative, and then when we were doing this velocity initial was in the y. So cool, that's going to be, yeah, I'm saying this is d. So yeah, so I'm going to say this is negative d in my calculator plus or minus the square root of d squared in my calculator plus, I'm just going to do negative 20, and then the height of, what's our first one? Our first one is 12 meters. 12. Cool. And then all divided by negative 10. I'm going to try to crush that out as fast as possible, but I'm going to do an all divided, so I'm going to do a parentheses there. So negative d plus the square root alpha d squared, and then I'm going to do negative 20 times 12, all divided by negative 10. Cool, and that gives us what we kind of wanted. I'm going to store that actually, well, I'll store it as O. You know what I mean? So this is going to store as O. And then the other component was when this was 18. And but I think we needed to use the negative one. Cool. So we use the positive root for T1, and for T2 we're going to use the negative root. And I'm going to store that as alpha n. Cool. So now we have what's our, how did d change? Because we're trying to get to see if d increased, then this was a positive. Like we can reduce our, we chose a initial velocity u, but we know if we increase the angle, then this d increases. Therefore, we can reduce that initial velocity. So that's, I don't know, I really like to do maximizes and minimizes problems like this. Like choose something. Choose a scenario and then change it by a little bit, and did it improve? I think if you can see the improvements, it's way better than just doing it from, I don't know, like a calculus perspective. Alright, hell yeah, I need to take a break, but we are squirming. Let's do this. Cool, so D is going to be that velocity initial, which I called E, and then the time, which is n minus O. So cool. So I have alpha E, and then the time difference was n minus O. So we have time 2 minus time 1, and then multiplied by that initial speed, which we calculated as 5 point. So cool. And did that increase? No. So that decreased. So now let's go the other direction. You know what I mean? So now I'm going to go alpha u sine theta minus 1, store that as alpha d, and then I'm going to go alpha u cosine theta 1, store that as alpha, oh bummer, my calculator ran out of juice. Alright, hell yeah. Alright, so we're back. I took a big break, and but I think, let's see, do we have these in our calculator? Yeah, didn't we do it? Oh, no, I don't. Okay, so this is cosine. U cosine theta minus 1 is 5.6. And we're going to store that, we're going to store that as alpha E. So we have alpha D and then alpha E. Cool. So now we're going to put these into our equation. And so to get the first time, we're going to have the upward trajectory. That's going to be D. And then we're going to have the first height, which is 12. The second height will be 18. So we're just going to go up to that equation. We'll do the 12 one first. And then booyah. And then we'll go to the 18 one. So hell yeah. And so, I mean, we did enough intuition for this, and then laid out, like, so now that I'm using the equations, I can still kind of refer back to, like, where these come from. But I think that's difficult. The second you see, like, a quadratic equation, you're just like, well, what are the inputs? How are the inputs giving me this answer? Okay, so I'm going to store that as alpha j, and then we're going to store this as alpha I. And just because I did time for t, and I probably put those in the wrong order. Like, there's t, there's s, there's o, there's n. So yeah, I put those in the wrong order, j and I. So I'm going to go j minus I. That's going to be the 2 times t2 minus t1. And then we're going to multiply it by, let's see, alpha e. Is that where? Yeah. So this times alpha e. And guess what? We get a larger number. So that's what we were wanting. Okay, so we get 10.4 meters. What this means is that we can reduce our initial velocity. So we had 2 components that had a resultant, and so this was our initial velocity, just kind of the magnitude, the vector of it. Has a magnitude and a direction, that's the direction, and it has a magnitude. And so that magnitude can be reduced. So the magnitude of this initial velocity can be reduced because this can be 10. Cool. Alright, hell yeah. Now, it's kind of interesting, like what? And all this says is what is the initial velocity. That so that's interesting because it seems like if you choose an initial velocity, you're choosing the angle as well, right? I don't know. I mean, it seems like if you do have an initial velocity that makes this problem minimum, you're also choosing the angle at which you are, so it seems almost like what's the angle that, I don't know, those are, I don't see how those are like one and the same, but it seems like they are. Alright, hell yeah. Alright, hell yeah. So I'm gonna try something that also I like to do, especially if I have, you know, at my ready the calculator, and I can change the angle. So the angle was 75, and we said if we reduce the angle. So now I'm going to do an angle of 60. So I'm going to go alpha u cosine 60. I'm going to store that as alpha d. Then I'm going to go alpha u sine 60, and then store that as alpha e. I'm going to go up to find my two different times. So I'm going to go back to these equations. Whoops. Oh, this doesn't give me a real answer no more. Wait, what's alpha d? 10.3? Why isn't that working? Let's see. Alpha u is 20. Alpha u sine 60 times alpha u. Stored as alpha d. So yeah, I probably just had that wrong. And then alpha, yeah, I had that wrong. So alpha u cosine 60, that's what we're going to store as alpha e. So alpha d is 17.9, alpha e is 10.4. Cool. And let's see, yeah, and now let's pull up that equation. Hell yeah. And then pull up the other one, just because I know they're going to work. Alright, so 18. And we see we have the minus there. The quadratic, this is going to be a plus square root. This is going to be a minus the square root. Okay, so that gives me a non-real answer. Okay. So yeah, so I can't get to 18 meters with that initial velocity. So let's hell yeah. So our initial angle was 75. Let's reduce it to 65. So we're going to go alpha u cosine 65. We're going to store that as alpha e, and then alpha u sine 65. Store that as alpha d. Whoops, store that as alpha d. Alright, pull up our two equations and see if we actually get answers for these. Nope. So, yeah, so this is negative 20 times 18. So we have negative, negative 20 times 18 is negative 360. Alpha d squared is less. So, so this, we might be stumbling across like where it's maximized. So let's, I don't know, let's just do more guess and check. So we're going to go, so this angle of 75, we're not going to go to 65, we're going to go to 70. So I'm going to go alpha u sine 70, and that's going to be 19.43. Square it, and that's going to be 370. All right, so now let's work in reverse. So if I have 360, the square root of 360, so I'm going to do the square root of 360. That's going to be 18.9736. And now I can see that this, because what I took u and I did alpha, so I took the initial velocity, which was given us, 10 meters at this angle, and I'm going to reduce the angle, okay, and I'm going to have two different components, but then they're going to hit these 2 points, and the separation is going to be greater than 10 meters. So I don't know if this is actually stumbling on like an actual, but it's worth following, so that's what we're doing. Cool. So alpha u sine of the angle, let's say it's 70, is that, okay? And if I take u sine of the angle, I'm going to get this, 18 point, Well, it's the square root 360. So to get this angle, I'm going to take the square root of 360, divide it by this initial velocity, which I'm putting as the letter u in my calculator, and then taking the inverse sine. So cool. So the inverse sine of the square root of 360 divided by alpha u gives me an angle of 66.54. So I'm going to store that as alpha z. And so now I can go alpha u sine alpha z, store that as alpha d. Let's run it in my calculator just because I don't know if it's rounding, on one side or the other. It's still, no, it doesn't give me an error, so that's good. And then I'm going to go alpha u cosine alpha z, store that as alpha e. So I have my alpha d, alpha e. Let's at least just get this. This is the time, 1.889 seconds. That's going to hit when it hits the second point. I'm going to store that as alpha j. And then we're going to pull up the other one. Cool, and this is the time to hit the first one. Store that as alpha I. So alpha j minus alpha I times alpha e. This gives me 9.01. And no, that was considerably less. So that did not help, and that was nothing. So apologize about that. But yeah, that was just a lot of wasted effort. Alright, I don't think I made a mistake, but let's try this out. So here is the angle. I'm going to reduce it by, I'm going to go alpha u sine theta minus 2 degrees. And I'm going to store that as alpha d. And then I'm going to go alpha u cosine theta minus 2. And then I'm going to store that as alpha e. I'm going to pull up those two equations because my equations might be totally wrong now just for whatever reason. I'm going to store that as alpha t, pull up the 18 one and store that, and then store that as alpha s. So alpha s minus alpha t times alpha e, and this is greater. Okay, so because we have this process, why not just keep going? So I'm going to go, and so just alpha u sine theta minus 5, stored as alpha d. Alpha u cosine theta minus 5, stored as alpha e. And then I'm going to pull up this equation, stored as alpha s. And then this equation stored as alpha t. So now I'm kind of a little bit faster, and then I'm going to go alpha e, alpha s minus alpha t, and that's getting better. Okay, hell yeah. This is the largest number that we got. So let's keep doing that. So I'm just going to take this one, and then I'm going to put 12. Well, it's let's do 11. Oh, bummer. Okay, and that got stored, and then we're going to do the other one and get this to be 11. Okay, and that got stored. And then we're going to pull up these two equations. So yeah, that's not going to work. So at some point this doesn't work. And so let's pull up this one. Whoop. I guess I'm just playing around, you know what I mean? But let's go 8. 8 degrees. That's stored. And then let's go 8 degrees. That's stored. Okay, let's pull up this equation, see if there's an error. Nope, there's no error. Let's pull up this equation. Cool. So now, and then let's pull up our solution. Our solution is this one. And it's less. So, like, even this right here, we played around with this where, what did we choose? 5 was sweet. 5 was the sweet spot, right? Yeah, 5 was killer. 5 said it was like 11 point something, so we should probably keep tabs on that. Yes, 11.27. 11.27. So let's go 6. And we'll do this just kind of one more time, maybe. Alright, hell yeah. pull up the t, pull up the s, and then pull up the equation. So that's not bad, just doing it manually. And this gave us 11.23. Okay, so hell yeah, I think I'm going to stop at that minus 5 because that was minus 6, right? So we have theta minus 5. I'm going to say at an angle of 70 degrees, that's going to be maybe our primo angle. The only issue is that our velocity is too high. You know what I mean? So if this is our angle, we actually need to bring our velocity down, and then that actually might change things. So there is more to it. So anyway, now I'm going to try to solve. So I'm kind of satisfied with like, hey, I think the answer is close to 70 degrees. And we kind of proved how an angle of 45 degrees that just barely touches 2 isn't the best, because you can go steeper and hit that and get that same distance. That distance is going to open up at the beginning and open up at the end. So, I don't know. Now I'm going to, this is the part of the problem where I was just hoping this would actually converge on an answer. But it is a lot of kind of guess and check. And so, yeah. All right, let's stick with this one. You know what I mean? Let's try to gut it out. So let's go back to what our distance equation is. Our distance equation is based on the time it takes to get to this first, point. If I know the time it takes to get to point 1, I can multiply it by the velocity in this direction that is always constant. That's the velocity in the x initial that never changes. And then I can find the time to get to the second point, t2, and then also multiply by the initial velocity. That gives me this distance out here. If I want to find the distance between these 2 points, I take this distance minus this distance. It's the difference. And so this is going to be the equation of the velocity initial, and then the difference between the 2 times. Time 2 minus time 1. Cool. So we found this will give us it, maybe. Don't know yet. But and then what? What are the equations for T1 and T2? That was the quadratic equations. And so, that was basically this equation. So we were saying T2 is the height of T2s. Yeah, so that's the height, y final. So there you go. So T2 is going to be negative, this is b squared, so it's going to be negative the velocity initial. Yeah, so it's going to be the velocity initial in the y direction, and T2 was going to be the negative one, right? It was going to be the negative root. So we have minus the square root, and then we have v initial in the y direction squared, plus, this is the v initial squared plus or minus 4ac, where a is just 1/2 g, so that becomes 2g. So that negative 20 is going to be there. That's, well, it's I can put negative 2 times g, where g is negative 10. So there's going to be 2 negatives there. Oh, yeah, and did I mess? Yeah, this is the minus 4ac I always mess up. Don't forget the negative sign. The 4 is positive. The a is going to be g, so you got negative 4g. The c term is going to be negative y initial, and then so you're going to have negative, negative, and then a negative 10. So this whole thing is going to be a negative number, and so that's what we have right here. It is a negative number. But we have negative 2g, and then we have a negative y, and this is final, y final. Apologize about that. Y final at time 2, which is that 18 meters. Okay, this feels brutal for me, but no, we're getting it. We're, you know, I mean, just doing the quadratic, and hell yeah, divided by 2a. A is 1/2, so 2 times 1/2 is just 1, and then g. So we have g down here. It's going to be a negative 10, but that's what that looks like. So, and this is t final 2. T1 is going to be, everything is going to be the same, but we're going to have a negative y final 1 at 0.1. Okay, hell yeah. So I didn't really realize this, but a lot of, like, isn't a lot of things going to be the same? You know what I mean? Because if we, if I have the number 2 and I'm going to subtract the number 2, hey, that's 0. You know what I mean? So if I have this value in T1 and I have that value in T2 and I'm going to subtract them, those go away, right? You know what I mean? And then so we can still keep this g under here, or T2 minus T1. Now I'm chill with that. You know, we're going to add the numerators. So if we do T2 minus T1, we're going to have a g downstairs. But then we have this. We have the square root of v1y squared plus negative 2g negative y final 2. And then we're going to subtract it by the square root of v initial y squared. Sorry, this is squared. Plus negative 2g negative y final 1. Okay, and this is just all divided by g. So that's T2 minus T1. And then we're going to multiply it by Vx1. Alright, hell yeah. And then sometimes I never know like how hard these problems are. You know, that's why I just did a lot of intuition just to like guess and check to be like, hey, we can probably get there. But what we're running into is that we have v, you know, we have the velocity in the x direction right there, and then we have the velocity in the y direction right there. So, I mean, basically what we need to do is say, hey, we're going to have some sort of velocity initial. Cool. And that's going to have two components. It's going to have a v initial x and a v initial y. And then those are related by this angle. So, you know what I mean? That's how we said that this angle is important, and this is why it is. Because we are, like, what do we're trying to minimize, we're trying to minimize the velocity. So that's interesting. So if we said that, well, if you take the hypotenuse, the bigger number, and take the sine of the angle, you're going to get VIY. So there you go. So everywhere where I see VIY, it's this, V initial sine theta. Everywhere where I see VIX, that's going to be V initial cosine theta. And now I have everything in terms of VI. And an angle, I guess. So is that two parameters? Like if I find an angle that minimizes well, I don't know. Yeah, that's what hung me up. All right. Okay, hell yeah. I'm just going to throw out terms, but yes, the change in velocity. If we do find a maximum or minimum, the change in velocity initial, the change in the initial velocity, if we do change that initial velocity relative to the change in angle, is this how we say it? This is going to be 0. Because if we find, how does this work? If we find the sweet spot where, like, because we just changed the angle. Like we set up a problem where we literally said, the angle, we thought the angle, you know, pretty decent approximation was fairly steep, 75. And then, you know, we got a distance of 10. between those 2 points, between on the way up, point 1 and point 2. Cool. We reduced the angle and kept the initial velocity the same. So that's, hey, let's change the angle and then ask how much does the initial velocity change. So that's going to, this is the derivative, you know what I mean? So the derivative of the equation. So if we have initial velocity as a function of the angle, then what I want to know is that if I change the angle a little bit, how much change in initial velocity am I going to get? And so we found that if I lowered and that's not what we did. Change in velocity. No, we changed d. Yeah, so that's what we did. We changed the angle. Yeah, we wanted to know what the change in d was. Change in that distance d. I'm just going to call it dt. As we changed, what did we change even? We changed the angle. Ah, shoot, I thought we were on to something. I think we need to take another little pause. Alright, now this might be right. So if we have d, is this equation. And this is a function of the angle. So we basically have d as a function of the angle. And then what we said is if I change the angle, this d is going to either increase or decrease. But if we find the maximum or minimum, hey, the d is going to increase, and then decrease. And right at that point where it increases to decreases, there is no change. That's the height of that graph. And if you take a small change in angle, there's just no change in that distance d. So that's a change in angle, no change in that distance d. So that's what we have. So we have this equation d is going to be t2 minus t1, which is all of this, multiplied by vx initial. So we have vx initial. So that is d. And cool. And then we can write this. And so, yeah, I don't mind just solving this on the calculator, compared to... So, yeah, let's do it. So we have d is equal to vx initial. What do we say that's going to be? That's in this direction. That's going to be v initial cosine theta. And then we have v initial, which is v initial in the y direction. That's v initial sine theta. We're going to have this squared. And then I'm going to get rid of the negative sign, but we're going to have plus g, and then y final 2, and then we're going to have the square root of that, minus, and this is going to be v initial sine theta. That's going to be all squared. And then this is going to be same thing, plus g y final 1, hell yeah, all divided by g. And there we have it. So we have d as a function of theta, and this should give us the angle. But that's not really what we wanted, was it? I mean, we wanted to actually know what v initial was. But if we found the angle to this equation, don't we find v initial? That's what I didn't know, you know what I mean? Because it seems like there's two variables going on here, but I'll give it a try. Yeah, I'll give it a try. Alright, hell yeah. So, I don't know. Yeah, this is interesting. Because don't I have to choose the velocity initial? Don't I already have to know that? That's kind of what makes this a little bit weird. Alright, so we took a huge break, and what we did in our spare time was we took the kinematic. Alright, hell yeah. And I think this was the results from it. We got an equation, but we can walk our way through that. And so and let's get some fresh looking paper. Okay. Booyah. And so, let's see. So we're going to have, we were saying that, I want some sort of steep trajectory. That's what I was, anticipating in the beginning. Kind of explored that. We're going to have a height of 12 and a height of 18. And then what we're trying to do is capture this on the way down. So that's going to be 0.2. This is going to be 0.1. This is 12 meters up. This is 18 meters. And so I need the time. And then what? Yeah. So what do I need? I need and I need to pick. No, I just know that I'm going to have an initial velocity in the y direction, and I'm going to have initial velocity in the x direction, and that is going to have a resultant that resultant is just going to be the velocity initial. You know what I mean? So this is a vector, and this is its x component, y component. Cool. So this would have a magnitude of vxi, well, I don't know, I hat, and this would be j hat maybe. But anyway, cool. So, well, what I need to find is the time it takes to get to point 1 and the time it takes to get to point 2. And so let's run through the kinematic equations from, just the fact that the acceleration in the y direction is going to be g, and that's going to be negative 10 meters per second squared. And if this is the acceleration in the y direction, I can say that's the change in velocity in the y direction, dt, and then this is the differential equation. You know what I mean? This relationship, this change in velocity, change in time, is a constant. We can use the technique of separation of variables to find a solution to this. That's the tricky thing about differential equations, is that depending on the differential equation, you're going to have to go down rabbit holes of figuring out how to solve for a solution to that differential equation. That's why I think it's very useful just to throw a number at it and then have that change take place, and then see if what changed, and then throw a new number at it. Okay. But if I separate these variables and we get a dt over here, I'll have dvy is equal to negative 10 dt, and I can integrate. And is that how you say it? Do you integrate both sides? I don't think so. I think you integrate this, and then you say that this is the change in velocity. This is velocity final minus velocity initial is equal to the integration of negative 10 dt. And so I don't know. Or you could do it this way, just say, hey, integrate both sides. I don't know if that's technically the way to say it, but I'm going to get an equation for velocity of y as a function of time, and then I'm going to have over here negative 10t plus my constant of integration. At time 0, I'm going to have a velocity in the y direction of vy initial. So if I throw in a 0 here, I'm going to have the velocity is going to be vy initial. This constant has to equal vy initial. So my equation for the velocity as a function of time is negative 10t plus vy initial. I can do the same thing. I can say that the velocity is just change in position, change in time. The change in position is in the y direction. And so I can separate variables, do that same thing. When I integrate this side, I'm going to get an equation for y, the height of this projectile, as a function of time. After integrating this side, because we'll do this and integrate, I'm going to have, and this is just gt plus vyi. So instead of calling this 10, let's just call it g, and g, just so we can keep track of that. And then so when I integrate this, I'm going to get 1/2 gt squared plus vy initial, the initial velocity in the y direction, times t plus a constant. And at time is equal to 0, if I throw a 0 in there and a 0 in there, my initial, and at time y is equal to 0. What's my position? At time is equal to 0. In the y direction, it's 0. I'm going to put the datum right there. So this is the x, y, and there's the origin, and so that's 0. So this equation is equal to 0. This part 0, this part 0, so my constant of integration is 0. So now we have y as a function of time. is equal to 1/2 gt squared plus the velocity y initial times t. And I need to solve for t, because I'm going to throw in the height at point 1. So I'm going to say y at point 1, you know what I mean? And so to rearrange, so that's this. So I would say y at, when it goes through point 1, is equal to 1/2 gt squared plus the velocity y initial times t. If I'm going to solve for t, let's get this to the other side, and I'll have 0 is equal to 1/2 gt squared plus vy initial t minus y1. And at the same, if I want to figure out, the height at y2 is 18 meters. I can do that same equation. I'll just have y2 minus y2. Okay, so the solution to both of these, if, y1 is equal to, not equal, but, let's just, so I'm going to use the quadratic formula that x is equal to negative b plus or minus the square root of b squared minus 4ac all divided by 2a. And I'm just going to substitute t in here. So t is equal to, the b component's this, so we have negative vyi plus or minus the square root, this squared, vyi squared, minus 4. The a component is 1/2 g, and the c component is negative, it's going to be negative y1. Cool. And so I can say that this negative is just going to be a positive. So there you go. And then that's all divided by 2a. This is a. 2a is just g. All right, so this is t1. T2 is going to be the exact same thing, except I'm going to have a y2 here. And then when I get the time to, this point, I'm going to use that to figure out the distance in this direction. So what is the position of this point in the x direction? Its x position is going to be the velocity initial in the x times t1. And the distance to this point is going to be the velocity initial in the x times t2. The difference here is going to be d, and we want that to be 10 meters. That's going to be this minus this. They both have, they're both a function of the velocity initial in the x. So I'm going to say d is equal to velocity initial x and then t2 minus t1. So I'm kind of just going fast because it's getting to be the end of the day and I want to kick this one out. And I don't even get like a really good solution. My solution is still a guess and check approach, but I'm satisfied with it. All right, so, and then this is T2, and this is T1, you know what I mean? So this part of T1 is divided by G, this part is also divided by G. This part's the same as this part, so when we subtract those two parts, those go away. What we found is that I was going to use the negative root to get this point on, T2 instead. So T2 could either be right there or right there. I'm going to go, you know what I mean? But if I'm going to say this point is right there, then I'm going to use the negative root for T2. So I'm going to have a negative here, and then if I want this point for T1, I'm going to use the positive root. And we just found that out by exploration. All right, so this equation D is going to be Vx initial, and then T2 minus T1 is going to be the square root of Vyi squared plus, I'm just going to say this is 2g y2, and we said that was going to be the negative root. So I'm going to have a negative here. I'm going to subtract it from a positive, so I'm going to have a subtract from the positive, which is Vyi squared plus 2g y1. And I've messed this up every different way you could, but this is correct now. You know what I mean? And then this is going to be all divided by g, and because this is all divided by g, it can be, and yeah, so now we have the full equation. So what I did is, let's set this equal to 0 by saying 0 is equal to negative d plus And that's what I have in my calculator. So I have negative d. And then what I also did is said, hey, if this is the x component and this is the y component, and I have an angle here, theta, then the x component is just v initial, whatever the magnitude of that is, cosine theta. That's going to be vx initial. And vy initial is this initial velocity sine of theta. So I go put this value in right there, and then this value in right there and there. So we actually square this value. So that's what I have in my calculator. And now I have a problem that's equal to 0. D is going to be 10 in my calculator. G is going to be negative 10. Y2 is 18. Y1 is 12. This G is negative 10, negative 10. And then this becomes VI sine theta squared. And this is VI sine theta squared. And then this is VI cosine theta. So that's what I have. And the theta is going to be my variable. It's my variable x. That is what I can... No, it's not. Sorry about that. The velocity initial is my variable x. This angle that pops up in all of these, I just put it as a variable r. I could have put theta. I just didn't know if it was going to work in my calculator. But I used this letter r. And then I just changed it. So in my calculator, this was my initial guess for my angle. And then I would change it. I would just say, hey, let's do -1, and then store that as alpha r. And when I did that, I would put r into this equation, we would graph it, and then we would find where it crosses. And what that does on this equation, if I'm choosing the angle, and then I'm basically solving for that velocity initial. I'm sorry, I'm not going to write that out. And then that came up as like 20.411248. And when I threw in values, so here's what I did. When I threw in a value of this angle of 75, and then I subtracted 7, and then threw it in, hey, I got this value. And then I subtracted 6, I get a lower value. And that's what the problem stated. The problem stated, what is the lowest velocity that you can reach these 2 points, and having these points having them separated by a distance of 10 meters. And so by changing the angle, then I changed it to, I probably went too far, to -5, and that was 0.4275. And then at -6 it was 0.4, hopefully I didn't. Oh, no, yeah, we kept going. So this direction, it got bigger, and we don't want that. We want a lower velocity. So I went 6, and then I just put in -5.6, and I probably got that value. It was lower. Who knows what those were. And these all have 20 in front. So I went from -5, so -7, wrong direction. Taking that angle and subtract, or that was too much. That was too much. And maybe -6 was too much. And so I did -5, and this number gets smaller. Then I did -4, and instead of 0.42, it goes to 0.41. And then I went -3, and I got, it was not nearly as good. So then I just went -9.395. And then that was the lowest number I got. So if I took this initial angle guess minus -3.95, that is the value, that's the angle that I got. So with that angle, 71.28, the lowest velocity I could have was 20.411248. So 20.4, just call it that, 20.4 meters per second is the lowest velocity that I could come up with to do that. Now, because you can hit different points on these, like these points could be right here and here, I think it works out that you want to choose the points that are up and over. I think we established that. I don't know, but I could be wrong about that. But this is the way I solved this problem. Not very nice. It doesn't allow me just to keep plugging in different heights, you know, and different values of the distance. It seems very particular to this. So, well, no, I guess not. I mean, I have this as my equation where I can throw in any value of d. And I can throw in any y value in y2, and this equation won't register on the graph if this is a negative. If there's a negative under the square root, it won't graph. That's why you have blank spots missing. And if the equation doesn't go through the origin, then there is no velocity that can actually hit those 2 points with that given distance. But with this, you have an equation that I can put in a height for that first one and a height for the second one and a distance between those. And then I can just choose the angle that I want. And then, you know what I mean, if your angle is going to be from 0 to 90, you know, choose 15, 30, 45, 60, 75, 90. You know what I mean? And then there you go. And so I think that's going to be the take home, is a lot of students don't want to do that. They don't want to be like, okay, I have an equation, but I don't want to put in 15 degrees, 30, 45, 60, 75. I don't want to do that. I don't want to do like five tries just to see, you know what I mean, what the answers might be. But hell yeah. So yeah, that's the way I solved it, and I have no idea if it's the right answer, but this technique can get you right answers way cleaner, I think, than just a pure mathematical, especially from pure math and then wanting it to be so simplified. You know what I mean? So this, I couldn't get to simplify. I'm sure there's just a hella simplified answer. I'm going to take a day to think about this, or maybe just look at an answer. But this is the video I put out. This is my solution. And I don't know. It just shows you that you can find solutions with a minimal amount of knowledge and just kind of guess and check approaches. The guess and check is what calculus is doing. So, you know what I mean? Like, I think that's it's a good thing to practice instead of just wanting the pure math, you know what I mean, like that pure equation, because you're going to get so many hiccups anyway, and real problems aren't clean anyway, you know what I mean, they're messy, and they're good to explore with them. Okay, so hell yeah, so I think I'm done. I think this was close enough to the answer. Thanks for joining me on this one. Hell yeah.